Nisa, can you make the second Geraldo? Can you spot it?
Sure, 1 second.
The one that is just Geraldo? The microphone, yeah.
Yeah, the camera, right?
I think that's all. Thank you so much, Nisa.
No problem.
I cannot hear you, by the way.
Not hear who?
I was talking to Nisa, but it was a one-way communication because the microphone here.
Oh, okay. Well, everything's okay?
Yeah, this is not the best I would.
Yeah. Let's make sure you're... Wait. Yes. The other slides? Yeah. No, I didn't get it. Shared it using Microsoft. Oh, that's... No, I didn't get it. I got your link for the panel. Okay. Gonna share soon. Oh, the timing. I don't time. Oh, do I need it? I'm not sure. Can people hear me in the back? All good? Okay, yeah. I don't need an extra microphone. Thank you, though. Yeah. Let's see, we can wait for a couple of minutes. We're missing our keynote speaker. This room is one of the easier ones to find, I think, right? Some of them are somewhere around the campus, I think. Is it? I haven't checked the other one, so I need to be at 2 more today, so yeah. Okay, they're all pretty close, okay. Oh, okay. Okay, that's good, yeah. Cool. So where should we stand for the live stream? Am I at the right place? Camera's okay? You don't need to move it. I'm in a good place? Okay. Right now, still I'm in a good place? Okay. Yeah. Okay, fine, don't touch it. It's like the DRAM mindset. If it's working, don't touch it. Don't disturb it unless something else disturbs it. Okay. I think we can get started. Okay, welcome to DRAMSec 2025. This is the 5th edition of quite successful DRAMSec workshops. This time I had the pleasure of organizing with Kuljit. Do you want to come here? Up to you. Kuljit Bains from NVIDIA. And I think this is the website. You can find all the information on the website if you're interested. Thanks, Kuljit. Yeah. Thank you. Yeah. This is our schedule. I don't want to take a lot of time because we have a pretty tight schedule and I want to have enough time for the keynote and the panel. And hopefully the discussions will continue over time. But I want to mention a few things. We have the keynote and the panel after this coffee break. And we have a bunch of paper presentations. If you haven't sent me your paper PDF, please send it to me. Otherwise, you'll have to connect to Zoom. Zoom is the best way. And then we'll have lunch. We also plan a dinner mainly for program committee and invited speakers, but there might be room to accommodate some other speakers also. So I'll have a show of hands later on. These are some of the workshop papers that we will cover. This is the program committee. We have actually a large set of folks who did a lot of reviews. Panel I'll introduce later on. We have 6 distinguished panelists, and hopefully we'll have fun discussing PRAC, existing solutions to Rowhammer, and how bad and how good they are. Okay, so dinner for those of you who are invited, and for those of you who would like to come, we're going to go to this Gompachi Shibuya, which Hwasong is responsible for. It took us a lot of work to figure out a good place that accommodates a lot of people, which was not easy, I should say. But it worked out, I think, in the end. You can see, I'm not going to read all of this over here. They can accommodate various dietary restrictions. The downside is at 9 p.m. So you'll have to work hard to get very hungry. And that's the good part. I think we can have DRAM discussions over there. So let me know if you want to attend. How many people are on the committee and are attending? Okay, just a show of hands. Oh, only, okay. Well, but there are other people who are over here also. So how many people want to attend, but they're not on the committee? Okay, so I see a lot of people who want to attend. That's good. Okay, please talk to me and Hwasong during the break, we would like a full count. So the restaurant is a little bit flexible. That's the good part. Okay, so before that, well, you can see some pictures, and this is the room they allocated for us. Okay, there are attractions along the way, which I'm not going to talk about right now, but I can talk later on after we have a good count. So we have some time to waste, let's say, from here to dinner. And Haosong has some potential plans. This is probably the easiest one, to go to Tokyo Metropolitan Government Building observation deck for free, which has an okay view, but easy. This is a little bit more expensive, but a better view, but a bit harder. So we can figure out what to do afterwards. And if you're a local and have a better suggestion, let us know. Okay, with that, I think I'd like to introduce our keynote speaker right now. We have Professor Moinuddin Qureshi from Georgia Tech, who's been doing a lot of work on memory systems and who doesn't stop working on RowHammer, even though he wants to. At least that's what he tells me. But I hope he doesn't stop working on RowHammer, for sure. Moina and I go a long way back. We were PhD students in the same group at the University of Texas at Austin during the same time, pretty much. He got his PhD in 2007 from there, and working on caches. And a lot of the work he did for caches. He continued working on caches at IBM Research, and a lot of the work he did went into power processors and maybe other processors that I don't know of, and maybe I don't want to know of. I think actually Z series has a lot of interesting things as well, right? And he got a lot of awards for his research, Morris Wilks Awards for more recently the Morris Wilks Award, but a bunch of Test of Time awards also for most recently the DSN Test of Time awards, which he cannot be there for because DSN is happening concurrently with ISCA right now on Avatar, which is a way of handling retention time errors in the presence of variable retention time robustly. And the Micro 2024 Test of Time Award for the utility-based cache partitioning work. But he's not going to talk about any of those today. He's going to talk about RowHammer and maybe tell us what we're doing right and wrong. And this will be a good segue for the panel as well, because our panel topic will be on this. But yeah, let's see. Thank you, Moin, for coming. Yeah. Welcome. Oh, I need to stop sharing? Okay, I can do that. Maybe. Maybe you need another chair. Oh, yes.
Thank you, Onur. I mean, Onur is right. Actually, before I talk about sort of the importance of RowHammer, right? So DRAMSec is playing a very important role. I would say that the last 4 years I've spent working on RowHammers primarily because of DRAMSec. It all started with an email from Stefan and Kaveh saying, hey, can you submit an invited paper? And I submitted a 2-page invited paper. I attended DRAMSec. I'm like, wow, this stuff is cool. RowHammer keeps worsening. Nothing works. People keep breaking. It's a problem that industry cares about, and there is no good solution. Architects love that stuff, right? So I would credit this workshop for sort of attracting me and sort of keeping me, right? And Onur's right that every time, I mean, Salman also laughs at me when I say this, that for sure this is the last RowHammer paper, but then a new problem comes, and then a new problem comes, right? So my hope with this keynote talk is to talk about what is needed to solve RowHammer, right? We have been at this for almost 10 years. DRAM industry has tried to solve this problem. It's not for the lack of motivation that we haven't been able to solve, right? So that I'm an academic, let me start with a pop quiz. What is the difference between painting and sculpting? Quick answer, sure. That's you. Anything else? Simpler. Think mathematical operations. Awesome. That's fantastic, right? A painting is complete when you can no longer add to it. A sculpture is complete when you can no longer remove from it. Typically, when architects think, they think in terms of performance, and performance is like painting. You keep adding feature, you keep adding until you run out of the paint. I contend that working in security is almost like sculpting. Your main task is to remove things that shouldn't be there, because anything extra that doesn't need to be there gives an attack surface to the attacker to break the system. And it requires a very different mindset, right? Removal requires very different mindset than addition. In addition, if you add something more, it doesn't really matter that much. In security, if any extra thing is there that you are not thinking about, you've given a door to the attacker to attack your system. Right? And hopefully this philosophy becomes clear as we go along. Right? So rowhammer has been around. I mean, it's a data disturbance error. It occurs when you access rows in succession, which leaks the data from nearby rows, causing them to flip. And this is not just a reliability problem, it's a security problem, because somebody can flip a bit at the page table and take over the system. And the big problem in rowhammer is that it's a moving target problem. When it was first characterized by Onur's group in 2014, the threshold was like 130,000 and it kept reducing to about 5,000. And we currently don't know. I mean, there are not that many publicly available characterization studies for DDR5, so we are really driving in the dark at this point. But in general, when we're developing systems, it's important to think about not just current threshold, but also if those thresholds reduce, what happens? How do you solve rowhammer? Basically, two parts. You identify the aggressor using some tracker, and then you refresh the victim rows. The intelligence typically in solving rowhammer is figuring out which is the aggressor. And that aggressor tracking can be done at the memory controller or at the DRAM side. If DRAM folks can figure out the aggressor at a low cost, it solves the DRAM problem within the DRAM itself. Nobody else has to worry about it, right? So it's an appealing solution if it can be solved at low cost. How does in DRAM mitigation work? Typically, within the DRAM chip, you have some small structure that keeps track of like which row and which row is likely to become aggressor. And then once you identify the aggressor, you still need the time to do mitigation. Now, DRAM is a synchronous device. It doesn't have, or at least did not have, ability till last year to say, hey, I want to take some time off. So the way typically mitigation was done is that you borrow a little bit of time from refresh, regular refresh, to do mitigative refreshes. Right? So the key challenge is basically how do you identify aggressors? And this again depends on the threshold. For example, if your threshold is, let's say, 1,000, and you can do about 700,000 activations to a bank within a refresh period, you can have up to 700 aggressors if you knew already, right? Now, you don't know which rows are going to get aggressors, so you need a little bit more entries, something like 1,400 entries. And people did this analysis. You need like several hundred or a couple of thousand entries per bank to identify the aggressor rows optimally, right? Pro-TRR method. The problem is that such large structures are not practical. Having 1,000 entry CAM per bank is just not a feasible solution. So what DRAM industry did is that, well, look, we can't give you 1,000 entry structure, but if we can give you a 4 entry or 16 entry structure, they developed a TRR-like structure. It had some counters. And the claim was that, look, we fixed this in DDR4 and rowhammer is not a problem. But of course, with a very small structure, these structures can break fairly quickly, right? And there was this paper from Onur and Kave's group, and then another paper on fuzzing that breaks a deployed tracker. And the basic idea was that, look, you have only a few entries. If I can target more entries, more aggressors, then your tracker cannot hold it, right? And then you'd still be able to win. And so it's pretty much now known that, well, all deployed TRR trackers can be broken. JEDEC acknowledges it. The DRAM industry took away from this that, hey, look, our TRR trackers were broken, so all TRR trackers are broken. right? And the overwhelming sentiment in industry and the governing bodies is, let's throw the baby out with the bathwater, right? TRR broke, so let's throw away TRR. But the right question to ask is not, did our design that was developed in secrecy and obscurity is secure or not? That's not the right question to ask. The right question to ask is, if you wanted a low-cost tracker to be secure, how should you design it? That's a different question. And that's an exercise I believe did not happen in the last 10 years, right? And that's, again, security by obscurity doesn't work. Right? That's where I think academia has a very important role to play. The best way to do security is not to say we did something we won't tell you, but rather to say, here is a design, go beat it. And if you can defeat it, more power to you. We'll all learn something. And the only chance of having something secure is if it's analyzed for some time and it still stands the test of time, right? So how do you design a tracker that's secure? And this is something that we did in collaboration with industrial researchers. In fact, this work started with my collaboration with NVIDIA while Guru Raj and Amir were at NVIDIA. And then it led to another low-cost tracker, Mint. When you're thinking about a tracker, we might not know the low-cost tracker, right? But we can actually abstract it out. You don't need to know the details. It has n entries, small number of entries. If you access, you can't really install whatever you access all the time. Why? Because, well, then it's a trivial to defeat design. I'll just overwhelm the tracker, you'll lose whatever you put in. So you can insert probabilistically. That's a source of failure. You can sometimes not insert if you're accessing something, right? So that's first source of failure. Second is when a tracker is full, you insert something, you need to evict something else out. That's where the eviction policy comes in. And the second source of failure is, hey, I sampled it, but the tracker kicked it out anyways without mitigation. And the third policy is, hey, you have n candidate. When there's a time to mitigate, you pick one and you mitigate. Which one? If you sample something and you kept it in the tracker for a long time, it can still get activations and it might actually reach the threshold. That's a mitigation policy. So that's a third source of failure, right? The problem with TRR-like trackers is the mindset was, hey, look, counters are important for optimal trackers, right? In fact, if you look at the literature, they would not say how many entries. They would say how many counters you have. Counters work very well if you have optimal number of entries. If you have only a few entries, counters actually give the attacker a very nice mechanism to fool your tracker. If my entry is there and you use counter-based replacement, I'll attack my attack row and then I'll attack a dummy row a lot. You'll kick out their row I'm actually attacking, right? You've given the attacker a powerful tool. So counters are harmful if you only have a few entries. When you're designing a small tracker, don't design it like an optimal tracker. Design it such that you give fewest ammunition to the attacker. Design it such that it's easier to reason about the threshold. And that's basically what we did. Our initial work, Pride, was at last ISCA, and then we followed it up with Mint. One of the basic insight in this work is at mitigation, you are going to select one entry for mitigation. How many entries are required in the tracker then? You actually don't need multiple entries. You really need that one entry that you're going to mitigate. Everything else is extraneous. Right. How do you select that one entry? A very simple, trivial design is, let's say we have a register that keeps track of that one entry. Sample address register. And what we would think is that, let's say, every time a row gets accessed with probability P, we are going to insert in this register. Very simple, straightforward design, right? If you access 5 items, all of them have equal probability of getting inserted into this register. This is what is IID sampling, independent and identical distribution. It seems fair, right? Because everybody has an equal probability of getting in. But it's actually not a secure design. Why? Let's say if C got sampled and got into the register. What happens if E also gets sampled? C gets kicked out. So in IID sampling, what you really want to be is in the last position. Nobody will kick you out. If you're in the first position, lots of items can kick you out. Even though this might seem fair, under our constraints of DRAM mitigation, it's not fair because there's a positional dependence on how often you mitigate something. You don't want positional dependence because the attacker is just going to attack the most vulnerable position. And the funny thing is when we submitted this paper to Micro last year, 2 of the 5 expert reviewers said, well, if the problem is evicting things out of the tracker, that's very simple to solve. Once you put something in the tracker, don't sample. You are not going to evict. Right? If eviction failures are your problem, don't evict. Right? So for example, if C gets sampled, don't sample D or E. This would be secure because you have no retention failure. The problem is, then your sampling probability is non-uniform. The last position can be sampled only if no other positions have been sampled before. Right? So this still has vulnerability, it just has a different vulnerability graph. In this, you want to be the first position. You don't want to be the last position. Right? So in both of these cases, there's non-uniformity. Ideally, you want is mitigation should have uniform probability of getting mitigated. How do you ensure that? Fairly simple. Don't use IID. You have n slots. You want to find one probabilistically. At the start of the window, just say, I'm going to select 17th item. Right? That's the basic idea in this minimalist DRAM tracker. Let's define a window of W activations between 2 refreshes. Let's say this window is about 73 activations. Consult a random number generator that gives you URAN, uniform random number generator. It gives you a ticket between 0 and 72. And that is your, that's basically the position you're going to sample, right? And then you count position 0. No, not a lucky number. Position 1, no, not a lucky number. Position 2, lucky number. We're going to sample this, store it in the address register, and then you can keep activations, doesn't matter. Nothing else will get sampled. And at refresh, you can refresh this. This is a provably secure, simple, single entry with counterless tracker. It doesn't have any retention failures. It has very bounded tardiness. Whatever sample, just you are going to refresh it. And it requires very low hardware, like 4 bytes. And we developed, like using certain properties, we developed the worst case. The worst case is actually fairly easy to determine. You cannot have copies of the row that you're attacking within the same window, because then they will get selected with higher and higher probability. For example, if you pack the entire window with 73 copies, well, you're guaranteed to get mitigated. So the attacker is restricted to having only 1 copy of the attack line within the window. And we use this pattern to determine the threshold that can be tolerated under a bound of like a bank failure rate of 10,000 years, 1 failure per 10,000. And the threshold, the double-sided threshold is about 1,400, much lower than current thresholds. And in the paper, we also show that this simple and I would say simple and minimalist design outperforms a 700 entry mithril tracker. A counter-based tracker is vulnerable to what's called fainting attacks. A randomized tracker isn't. So it's not that you really needed the counters. It's not that you really needed hundreds of entries. You just needed to define it, design it appropriately. Right? We also looked at refresh postponement. Refresh postponement, if refreshes can be postponed, then you basically are dealing with like your window being 73 instead of 73 is like 365. And the attacker can just postpone refreshes and break. And we developed a very simple structure, a FIFO queue that says, hey, when it's 73 activations, just do a pseudo retirement. Whatever you want to retire, put it in a FIFO queue. You just need a 4-entry FIFO queue. And whenever refresh comes, take the oldest entry from the FIFO queue. Right? So this is with refresh postponement. The first row corresponds to a per row counter table. If you have an idealized tracker that had a counter with each and every row, you get this. If you have a single entry counterless tracker, you get this within 2x. So the gap between a simple minimalist tracker and an idealized tracker is only 2x. It's not that much. Right? Simple trackers are possible, and they're actually pretty good. So it's not that TRR is broken or TRR needs to be thrown away like baby with the bathwater. You just need to design it differently, right? You just need to design with security from the ground up. So another problem that Onur's group brought up 2 years ago, and Onur's group has been phenomenal with characterization of DRAM, right? I would say his group is primarily responsible for keeping the DRAM industry in check. So RowPress happens if you keep the row open for a long time, and then there's a charge leakage, and then now you don't need too many activations to cause failure. For example, if you keep the row open for about 500 nanosecond, you need only half as many activations. Right? And then this is a problem. You design a tracker for a particular threshold, and now you need half as many activations to break the tracker. Right? And then again, you can solve again this with a minimalist mindset. You don't want to limit users from how long they keep the row open. DDR already has specifications for that. And we don't want to pay too much hardware, right? And still solve RowPress. How do you do it? Simple. If an attacker is doing RowPress, the attacker is not doing rowhammer. If you're keeping the row open for a long time, that means you're not continuously doing activation. Convert the row open time into activations. So if you're keeping the row open for 4 TRCs, think about that as 4 activations. Right? From a security analysis perspective, you're dealing with time. Whether you really don't care whether it is RowPress or rowhammer, you're dealing with time windows. So hey, if you want to keep it open, keep it open. We'll just assume that it's an activation, right? And we took this approach, and it's actually fairly simple to tolerate RowPress and rowhammer all with Mint. What you do is instead of counting an activation as one activation, you basically convert the open time into equivalent activations. So a row that's open for a little bit might be 1.5 activation. For a little bit longer might be 2.4 activations. The same algorithm works. You plug an index, but now instead of counting activations as integer, you count activations as floating point numbers, right? So the first one might end at 1.5. The second one probably need 1.3. So the addition is 2.8. Ah, you crossed 2. So that's the activation that you will select, right? And so you can solve both rowhammer and RowPress with literally a couple of bytes, right? But again, this is a design that's minimalist from the ground up. So changing the gears, the current state of the DRAM industry, last year, per row activation counters were released. And this is again a reflection of the inability to solve rowhammer securely and at low cost. If you can't solve it, even after given like almost a decade, what do? You think about, well, what's the most principled way of solving it? The most principled way of solving is give each row a counter in DRAM, per row counter. Second, hey, in DRAM trackers require time to do mitigation. They borrow time from refresh. Why don't we allow them to borrow or demand for time, paid time off whenever they need, right? So that was alert backoff. These are the biggest change to DRAM array and interface in a couple of decades, right? So it's phenomenal that DRAM industry is responding to this threat of rowhammer. I actually did not think that, knowing the constraints of DRAM industry, they typically are very, very resistant to change. So it's phenomenal that that's happening. So I'm coming, right? I'm coming. Super. Okay. Yeah, I'm coming. I'm getting there, right? Like, okay. So why PRAC and ABO exist? Again, DRAMSec gets credit. In DRAMSec 1, there was a paper called Panopticon that showed how per row counters can be used for solving DRAM rowhammer problem. In fact, per row counter, the actual idea is fairly old. Kuljit had a patent in 2012 on per row counters, right? And Panopticon showed that you can use per row counter for in DRAM mitigation. So this became the principal way of solving. And then there's been a lot of effort, I would say, from cloud vendors to make DRAM industry adopt this. As you can see, the emotions are high. when you put a lot of effort, that happens. So I understand that it typically doesn't happen out of the goodness of the heart of the DRAM industry that, oh, look, do this. It's really a pull, not a push. So how did, in case of ABO is channel-wide. When you assert an alert, you stall all of the banks. And you really don't want to do that. Like, hey, I have a row that needs mitigation. I'm just going to stall everybody, hundreds of banks, because I need mitigation, even if they don't have anything else to mitigate. So in per row counters, you need a few, you need a small SRAM structure to buffer up things that you want to mitigate, because then you're nice to your neighbors, right? Basically saying, I have a list of things that I want to mitigate. You also have a list. So when alert comes, we'll all have something to mitigate. Right? So a representative design is Panopticon has an 8-entry S54 queue with each bank. When the counter crosses a particular threshold bit, you insert in the FIFO queue, and then you drain the FIFO queue in order, FIFO order, right? Either under refresh, or if the queue is full, you trigger an alert. What I contend is that, again, even for PRAC, think about minimalist design. The moment you have large structures that have extra things, you can break this kind of system. For example, if you have a FIFO structure, 8-entry, what the attacker can do is just access 8-entry continuously. These 8 entries will come in the queue. And now you know that these entries were going to get taken out of the queue in FIFO order. Start hammering the youngest entry. Change the pattern and attack H all the time, right? And now you've given the attacker time to actually do activations, right? So in a FIFO design, you can cause almost 8x more activations than a particular threshold, right? So how do you design this securely? Again, the principle remains the same. On a mitigation, if you're going to mitigate one entry, why do you need multiple entries? Just have a single entry, right? The one that you're going to mitigate. Everything else is extraneous. Which entry should you track? Actually, the worst entry. How do I know the worst entry? Keep track of the counter in the SRAM entry. So if you access something that has a higher counter value, go track that one in the SRAM queue, right? So you basically always track the worst row that you have seen since the last mitigation. If it crosses some alert threshold, trigger an alert, if the count, and then another alert, basically mitigate whatever you're tracking. That's all, right? It's a simple minimalist design, and again, designed to mitigate one aggressor per alert. And this was work done around last summer, so with Salman, and this is a provably secure design for PRAC plus ABO. How does this work? Let's say alert threshold was 64 activations or 128 activations. With 64 activations, you at least see a few alerts. With 128, basically, you don't see any alerts. The slowdown from mitigation for alert threshold of more than 128 is virtually zero. And when I present this slide, the common response is, we don't have alert threshold of 128. Why are you talking about this? I said, I'm not talking about this because I think that the thresholds are 100. What I'm showing is that the point at which the overhead goes from non-zero to zero. Guess what will happen if I show this diagram with alert threshold of 256? Still the red line. 500, still the red line. 1K, still the red line. This graph shows all thresholds above 128. Right? What this is showing is that if I'm a DRAM vendor, put alert threshold as 128 or 200. It doesn't matter what your threshold is. You don't have to think about it. The overhead is zero anyways, right? So don't be so precise on what your rowhammer threshold is. At some point, the overhead becomes zero. You don't have to think about it. Right? So this is a very principled approach that reduces the cost of mitigation, right? How frequently you want to mitigate. But there's a catch. There's a big problem with PRAC. What? PRAC is like an insurance policy. It avoids paying if something bad happens. But the problem is that insurance premiums are high. When you want, I mean, the reason why PRAC works is when you do an activation, you have to do a read, modify, write. To support that read, modify, write, DRAM timings are changed. So T-pre increases from 14 nanosecond to 36 nanosecond. They've reduced the TRAS. The impact on TRC is about 4 to 6 nanoseconds. But that's still fairly high. And especially for like, if the row is open, servicing requests from a conflicting row becomes very long, something like from 40 nanosecond to 62 nanosecond. Even for closed plate system, the TRC increases more than 10%. Right? And this impacts performance. Why? Because every single access has to pay that latency. Now, there is a subtle argument here, right? There are a bunch of workloads in this red part. You'll see that, oh, look, the overheads is only 1%. If you were dealing with streaming workloads that are bus bound, PRAC doesn't impact the bandwidth. If your workload was bus bandwidth bound, PRAC will not have any impact. If you have a GPU system, PRAC will really have negligible impact. But if you're a server system where the CPU is waiting for the request to get completed, then PRAC overheads are high, right? And this is basically the system performance loss. I mean, this is a discussion that we've had from various groups that, look, PRAC affects bus bandwidth by 1%. Why are you showing system performance loss by 10%? I'm like, they're not in disagreement. If bus bandwidth is what determines your system performance, yes, impact will be 1%. If latency determines your system performance, it'll be closer to 10%, right? And this is something that multiple academic groups have shown independently, that PRAC overhead is somewhere between 8 to 10%. This is very high. And I don't know if such high overheads are acceptable when the cloud vendors know that, look, this solution is really good, but it's going to cost 10%. How do you reduce these overheads? So we like PRAC, but we don't want to pay the latency overhead of PRAC. The basic insight is, do you want to pay the insurance premium all the time? Do you want to do the counter update all the time? Let's say a threshold was 500. Do you really need to do the counter update 500 times to know a row that you have gotten 500 and then you need to do mitigation? What if you just did randomly, probabilistically? 10% of the time. 10% of the time you do an update, 90% of the time you skip an update. Now your overheads reduced, right? And you can bound this again, what's the mean time to failure from naturally occurring errors, such that the failure rate from this is no worse than naturally occurring errors. And we developed an in-DRAM scheme. This is going to be presented on Tuesday, where you can do this probabilistic update completely in DRAM. When a row is activated, you sample it, and you keep it inside a tracker, or basically a queue. And then under refresh, you do the counter update. If the queue is full, you basically trigger an alert, and you drain out multiple entries, right? So the premium paying happens under refresh or under ABO, not on each demand access. What does this buy? PRAC overheads are about 10%. If you do probabilistic activation at a threshold of 1,000, it's virtually zero. 500, it's about 0.7%. At 250, it's about 2%, 2.2%. Right? So this is a way to reduce the PRAC latency overhead. And then finally, this bonus part, I didn't know how much time I'll have, so I'll just take 2 minutes. I know that giving host systems responsibility for mitigation has gone out of favor. And this is something that we have been looking at. Does SOC-based mitigation still have a role to play? Why? Because, and then you can do this again with very low cost, right? Like para-like scheme. So the storage overhead is very low. What's the incentive for a SOC vendor to do this? If DRAM industry has solutions that they are not going to reveal, you don't know what, I mean, is obscure, right? Second, if your only choice is paying 10% for PRAC, again, that might become a not a very pleasing situation to begin. So this also allows SOC vendors to get matters in their own hands. DDR5 actually has support for this, called DRFM. In DRFM, each bank has a sampling register DAR. When you activate, when you're pre-charging, you say, sample this address into DAR, and then send DRFM, right? And DRFM comes into varieties, either all bank or same bank. So it stalls either 8 banks for mitigation or 32 banks for mitigation. This is different than the nearby row refresh that academics have used for evaluation before, which stalls only 1 bank. If your mitigation stalls 8 or 32 banks instead of 1 bank, that's high overhead. How high? If you stall only 1 bank at 4,000 threshold, current threshold is about 2% slowdown. 8 banks, all banks, so fairly high. How do you design a DRFM aware mitigation? This is something that, again, we'll be presenting a paper on Tuesday. The basic idea is delay the mitigation. When you sample, don't immediately send DRFM. You don't really have to send DRFM until the next time you need to sample, right? And delaying allows your neighbors to also sample something in their own bank. And if you do that, then your overhead is at about 1%. It's actually, with a clever design, you can get a low overhead that's even lower than para with nearby row refresh. Why is this useful? Why would a SOC vendor do it? For 4,000 threshold, the slowdown is about 1%. At 8,000 threshold, it's about 0.5%. Very low overhead for current threshold. This might not make sense if thresholds are below 1,000, but if it remains above 1,000, it's actually a viable solution for SOC vendors. To conclude, remember where we started, right? I hope that in this talk, it's clear that when you're thinking about security, don't come up with a solution and try to prove. That's usually a losing battle. You will have a solution that already has added parts that will make it hard to derive security. And even if you have sort of convinced yourself of a complicated solution that is secure, it's very hard to determine. Unless the model is simple, it's very hard to determine security, right? And that's why it's important to sort of come at it with a different mindset. What's the simplest thing that I can prove that can solve the problem, and start from there in terms of implementation. Right? So it's a very different mindset. You think about what can be proven and then go from there and then add something if it's absolutely sort of needed. But usually, what's the simplest minimalist thing that can solve the problem? So all of us are here because we care about DRAM reliability. TRR has been a problem. We want to solve it. The approach DRAM industry is currently taking is that TRR is broken, sort of has gone out of fashion. I would say that unless your thresholds are below 1,000, TRR is probably the lowest cost option for the DRAM industry to solve this. But to solve this properly, you need to design a principal tracket. There is usually, the disconnect tends to be that if you see a simple design, people tend to add to it because, look, I made it even more intelligent, right? Or even more performant. In security, if you take a simple design, the moment you add something, you've actually broken it if you can't reason properly. So have a design that's principled, provably secure. Don't add unnecessary, potentially insecure thing to it. PRAC is great. You still need to worry about how to design it securely. PRAC is great, but the performance overhead, the insurance premium that we have to pay per access is high. How do we reduce it? And again, my chats with industry folks make it seem like DRFM might go out of fashion. I would say, I would encourage industry to still keep DRFM because it does provide a potential way to solve the row hammer problem for SOC vendors without paying too much hardware. If you want to ensure security, minimalism is the key. It's a different mindset. And the biggest learning for me in the last 4 years has been that the mindset needs to be different if you're designing a secure system. Design for simplicity, design for provability. Finally, if you're working on reliability and security, everybody would want those, but nobody would want to pay the cost. So the challenge becomes, how do we provide reliability and security at low cost? Thank you. I'll be happy to take any questions you may have.
Good morning for the next keynote. Any questions? Good morning. Yes, please. You can try it. I don't know if it works. Does it work? Go ahead.
In a team where I usually try to calm both the security team and the performance team, because the security team is paranoid and the performance team does not want any of the mitigations to be implemented because of performance impact. So I have a few questions, and maybe your answer can help me convince the performance team. The first is when you say for DDR4, the hammer count is roughly around 5K. Is it 5K for every row, or are there like maybe few rows in every bank that see 5K? Usually the distribution is not as.
So Onur's group has done a phenomenal work. It's basically the worst case that typically matters, because it's very hard to reason saying that I have 5 rows, but I won't tell you which one and where they are, and they have the lower threshold, right? So it's determining row hammer threshold for each row at runtime is hard, right? But if you have few outlier rows, it's possible to decommission them and then have a remapping. So if you a priori at design time or like at boot time new, you can bypass. But at runtime, those rows happen. It's very hard to mitigate. So from a ensuring security perspective, can you ensure security even the worst case regardless of where that happens, right?
Still a big challenge for the industry.
So very good question. I used to think exactly in this mindset, right? And after interacting with people like Salman, I became very cautious. What happens is that we think in terms of, oh, this must be hard to do. Attackers, A, are creative. B, they have a lot of free time on their hands. They've right? So in security, even under sort of this idealistic model, it's hard to guarantee security. Saying that, oh, at runtime, I'll figure out what the thresholds are, and then tailoring it becomes hard, right? So I would say the right way to bridge the gap between the performance team and security team is to figure out low-cost solutions that work under assumptions that are not very strict. And that is probably the way to solve the problem. In fact, the whole concept of what's a row hammer threshold itself is all academic, because the threshold of a row, as Onur's group has shown, that also changes over time. So it's very hard to say this row's threshold is X, Y, Z.
Most of the times it's not successful, and then the performance teams come and say, hey, then why did we use it, right? So
this line is very important, right? Like I've been working in reliability and security for almost 20 years. In fact, at the start of my PhD, I had an option of working cache versus reliability. I went and did a summer internship at the best reliability group in the US, Joe Lemmer and Shubhu Mukherjee's group. And that convinced me that I should work on caches. Because my takeaway was that if you are fantastic, world's best leading reliability people, you're still sort of like in the role of sermonizing, hey, do this because bad things might happen. And people are like, oh, yeah, talk to us later. And if you have performance solutions, people will call you, hey, you got anything for me? And I want it to be on the other side, right? Now the constraints have changed. Reliability has really become a big problem, partly because we haven't paid attention. So it's important to pay attention. But again, figure out solutions that are ultra low cost. That's the only way to moving the needle, right? That's the reason why I titled this talk. If you want to move the needle, moving the needle in row hammer defense requires minimalist, ultra low cost solution. How do we get there?
thank you.
Yes, go ahead. So, very good question, right? If I were to be suggesting, and I'm not in JEDEC or anything, right? I would say PRAC was an overreaction because there was no way, like low-cost TR trackers were not available. It wasn't clear whether DRAM industry would do the right thing, develop the right tracker, and they would never reveal anything, right? Under that setting, what do? You come up with theoretically provable, even if it takes high overhead. I would say the work that has happened in the last couple of years have shown that TRR by itself is not a bad idea. TRR probably, in my opinion, is the way for industry for at least when the threshold becomes below 1,000, right? So it has a very long runway with the caveat that do it securely, provably secure design. Don't come up with obscure design that gets developed in like a dark room without telling anybody else. That's a way for disaster because everybody thinks that they are very creative and they will just add this randomized thing here and there, right? What has been presented, like Mint might look simple. It took several researchers, several years, and several papers in this area to get to that minimalist solution. To me, if a DRAM industry wanted to do something, not pay the storage overhead of PRAC, the cloud vendors don't want to pay the performance overhead of PRAC. The right thing to do is a probabilistic solution, right? In a world where costs are not a problem for SOC vendors and DRAM vendors, I don't know which world that is. I haven't come across that. Go with PRAC.
Okay, I think this is a good time to transition into the panel. Thank you, Moin, again for the keynote. You're part of the panel, so you can stay where you are.
Yeah.
Let me share my screen. And I'd like to propose people to ask questions. Asking questions. If you're not already part of the dinner, there's already a place in dinner. So you're welcome to join dinner. Oh. Okay, I'm sharing something.
You've seen all of this before, right?
Yes, yes. Can you bring some chairs? It gets better.
Yeah, I can imagine.
You don't need to stand it. Oh. Yeah, we have two now. 3, 4. Power parallel. Okay. Am I sharing? Is that me or?
No, I don't think so.
Academic.
Yeah, the academic is on the side. People with power. People with decision-making powers. Salman, this is also a spectrum.
Do I need the mic?
Academicness.
Okay,
I'm
Moin,
the
can I
wrong
have the mic from you?
Yes.
Are we gonna use this mic?
Yeah.
Okay, so we're gonna start the panel now. I'll quickly introduce our panelists and then briefly introduce what the panel's about. Why am I not? Okay, there you go. So we have Moin's talk was a good segue into this panel because we're going to discuss exactly what he talked about, and he expressed his opinion that PRAC is not a good solution, at least the way it's implemented today or proposed today. Let's say we don't know the implementations, in my opinion, but there are differing opinions on the topic. So we have Kuljit, who is the organizer from NVIDIA. We have Jeremy from Micron. I think I'll ask people to introduce themselves very quickly when they make their opening statements. We have Salman, ex-Google, now independent, enjoying his time, let's say. And he's done a lot of work on RowHammer and actually has a paper here. And then we have Moin, we have Stefan from Microsoft, and we have Steve from Rambus. So what we're going to do is we're going to talk about this topic: is per row activation counter is a good solution to DRAM read disturbance? Are we missing anything? can we and should we do much better and hopefully not worse? Hopefully not worse, because we could do worse. Okay, so very quickly, PRAC is per row activation counters. Moin talked about it. This is standardized in DDR5 and probably other memory interfaces. We have a lot of read disturbance sessions at many conferences. You can take a look. Stefan knows a lot of these, I think. He counted hundreds of papers on RowHammer recently. Do we need all of those is another question that we can discuss if you want. More read disturbance sessions is S+, more coming at ISCA. Some conferences have multiple RowHammer sessions, which is good, I think, in my opinion. Okay, and we have papers coming up, 7 papers. This is actually the most papers we've had at DRAMSec this year, which is good. That means there's more interest on the topic. So what I would like, this is the email that I sent to the panel, our panelists. They're going to have a 5 minutes at most introduction statement that'll summarize their views on the topic. And they can also address other questions on DRAM read disturbance. We're very flexible here, as you can see. And we'll have a 45-minute panel discussion on the topic. The discussion will be dynamic, so we're going to rely on the audience. And I see some DRAM vendors at the audience also. We invited other DRAM vendors also, but I don't know. Is there anyone from SK Hynix or Samsung here? I cannot recognize anyone. Yes? Okay, wonderful. Samsung, okay. What about Nanya or any smaller vendors? Okay, that's good. Micron is well represented, which is great. Okay, yeah, yeah. Okay, and our goal is to maximize discussion. So hopefully the statements will be relatively short. Now, what I'm going to do is do a random selection of who's going to go first. Moin is going to go last because he talked a lot already on the topic. Let me see. Who should I pick? I'm going to pick Stefan. Oh, no, okay. You don't want it? Are you sure? Yeah, I think he's okay with it. Do you have the Zoom link?
Yeah, I have the Zoom.
Okay, if you want to join Zoom, that's the best probably. Oh, can I? Oh, you're already on Zoom. Okay,
Yeah,
share. Yeah, let me stop sharing. Okay. Can you share? Yeah, there's beer. So certainly people. Yeah. Yeah. Well, yeah, we have sponsorship, so we're going to cover the dinner. So we can continue this discussion over the day and over dinner. So, okay, Stefan.
Okay.
You can hold it.
Yeah. So there are a couple of things I wanted to say. First of all, one of the questions that I've been getting recently over and over again is like, now that we have PRAC or PRAC, what are you, meaning me, going to work on next? And actually, I'm very worried about this question. The reason why I'm worried is not because I don't know what I'm going to work on next, is because this question behind it, there is this premise that PRAC now solves RowHammer. And I really want to get this message away that RowHammer is far from being a solved problem, okay? And I have 2 messages in these slides. One is to researchers, and that is that there are many challenges and problems that still remain, and I want you guys to work on them if I think they're important, okay? And I think you're best equipped to actually fix them. And whether it's through a tracker or through probabilistic counters, through whatever it is, but there is a lot of problems left. And I'll mention a few of them very quickly. One is that PRAC needs many correct parameters configured correctly. And there is a long history of getting parameters configured wrong all the time, okay? So how do we fix this problem? And this is a great research problem in my mind. 2, PRAC resets row counters. So at some point, those rows, actually the counters are being reset. And there is this mismatch between you wanna reset the counter only when you know all the disturbance have been cleared. And there's no single point in time when all the disturbance has been cleared. So when are you going to reset those counters? Another important problems. Third problem, one of my favorite, is one row spans multiple DRAM chips. Each DRAM chip implements PRAC independently. And these counter values in each chip are out of sync. Okay, and I've made this point before. I'm not sure if people really, or I don't know if I'm communicating really well this point. So I have a short animation about it. So this is one row spanning 4 chips. Okay, this is just an example. And let's say these chips values, these counter values are 1,000, 2,000, 3,000, and 4,000. And here 4,000 means the highest, right? So at 4,000, let's say I want to do some mitigation. I'm just assuming. So what this happens is chip number 4 is going to require mitigation, whether that's alert or something else. I don't care. But chip number 4 requires the mitigation. Chip number 4 is going to mitigate. Then we're going to get another activation. So let's say another 1,000 activations. Now the counter values are 2,000, 3,000, 4,000, and 1,000. Does that make sense? Yeah. Now chip number 3 requires activation, and so on. This is actually a very inelegant design. So we have this defense implemented in each chip independently. And it's just, if you think about it from a principal point of view, it seems like a terribly inefficient design. Okay. Number 4, we need a rigorous security analysis for PRAC, which we don't have, okay? And many other things. Now, one more message to industry, actually, message number 2. I continue to hear from industry all sorts of claims about RowHammer, how it's going to be solved. And I'm going to talk about it on the next slide. Please stop making these claims that are unsubstantiated. Be skeptical. And I really would like to have no more surprises. Like surprise, you know, there was some other problem that, yes, the DRAM vendors or Intel worked on it for 20 years, but didn't tell anyone about it or something like that. No more surprises. So here's one thing that actually I run into. So one of the things is because I'm actually at Microsoft, I sort of also, and I'm in the research lab, so I'm an academic sort of by training, but I also spend a lot of time in industry. One of the things I hear these days is about vertical channel transistors. This is a slide from a memory workshop last year or 2 years ago, no, last year from Samsung. It's not important what the slide is. It talks about how, you know, as we go forward, we're going to have VCT, vertical channel transistor, and vertically stacked cell arrays, and blah, 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 4F² cell architectures, and so on and so forth. And one of the things I hear is, oh, VCT is going to be great because it's going to eliminate RowHammer at the root. Okay, we're not going to have RowHammer with VCT. I don't know. I'm not a DRAM guy. Maybe this claim is correct or not. But my take is you can't scale DRAM further without actually experiencing significant data integrity problems. And again, I've been here. I've done this so many times. I see the same thing, which is, oh, we're going to have VCT and something, and it's going to go away. I'm worried. I've seen these trends before. I think we need to take, again, this problem very seriously. So that's my message to industry, and that's all. Oh, there we go. I'm not aware about this.
We can discuss during the dinner.
Okay.
Yeah.
Okay,
Well, you can we can discuss during the panel questions. But thanks, Stefan, for covering a lot of interesting things. Who should I pick next? I'll pick Kuljit next. We start with Microsoft. We'll go with NVIDIA. Kuljit, do you want to share any slides or just talk?
I can start.
Okay, yeah, go ahead, please.
Yeah.
Kuljit has been working on RowHammer for a really long time, probably more than anyone else in this room. Longer than anyone else in this room, unless somebody finds Which is
As background, I spent about 31 years at Intel and last couple of years at NVIDIA. And we experienced this RowHammer back in 2012, first time around, when there were some database problem at a customer, and there were semaphore excesses that was beating up on the same resource. And the threshold was pretty high in those days. So there were different ideas explored. I mean, one of them was also a counter per word line. So this was done back in 2012 with a backup mechanism similar to alert. So that was one of the ideas explored like 13 years ago. And then memory vendors at that point said, well, we'll fix it. It's our problem. And we went down that path. But soon we found out those implementations in the DRAM were very simple, easy to overcome. And then there was the TRR command added. So TRR is not exactly the internal mitigation. TRR was a target row refresh command that came from the controller. A lot of the papers start referring to TRR as the DRAM mitigation. So that's kind of not the right thing. So TRR was never labeled as the DRAM mitigation. It was a command on the bus. And then there was enhanced TRR. So initial implementations were more simple counters, easy to overwhelm. And then vendors started using some probabilistic methods that are much harder to overcome. But still, I think folks started figuring out how things are randomized and may overcome that. So it's come a long way since that. And then controllers used to track and send out refreshes to the neighboring rows. And that would not work because the whole memory is not in one array. There are spare rows and the memory internal addresses are randomized. You don't know what the neighboring rows are. So to address that, DRFM was introduced. So DRFM is directed RFM, where controller tracks the aggressor, sends the address, and the DRAM knows who the neighbors are. Even if the addresses are internally swizzled, or the addresses could be in a spare row, because in spare row, the neighbors are not a fixed address. So the DRFM command got introduced. So, but over time, the memory vendors got tired of implementing probabilistic methods and not having a deterministic way. So that led us back to PRAC. PRAC was actually PRHT, perfect rowhammer tracking, but but the tracking is perfect. The solution, the mitigation may not be. So the industry went back and called it PRAC instead of PRHT. So PRAC, as a result, is going to be more deterministic, and the memory industry realizes there is performance overhead, there is some power overhead, but at least you address the security issue by paying this one-time tax. Now, a lot of these overheads are, I believe, overstated. So they're saying like 10% performance. We believe it's still in the 1% to 2% range. There are a lot of things that controllers can do to optimize around that performance. So the write row cycle times are not increased, read row cycle times have increased, but there are multiple banks to play around with, different paging policies, different interleaving schemes. So the performance overhead is we call it a one-time hit to address this issue and not deal with security or bit flips. But it causes another set of problems. We have the denial of service problems. If the alert is getting addressed, is getting asserted by the DRAM. So it's not a done deal. I mean, we need to still work around. And PRAC is not a precise spec. It's more of a framework for the vendors to count, have a counter per word line. How they address that in a FIFO, whether it's a FIFO or not, is not part of the JEDEC spec. So it allows vendors to prioritize things within the DRAM. It still allows vendors to repurpose some of the refreshes. And if the count exceeds a certain threshold, the controller can also send RFM. And that RFM in DDR5, I don't think will be widely used, but as we go to future technologies, there are things done to optimize performance. There's RFM per bank, RFM per dual bank. So you can hide a lot of this performance as we go to the next technologies. So it's not a done deal, but we need to make sure some of this vendor implementation are secure and we address the performance concerns.
Thank you very much. Take it. Okay. Okay, next, Salman, would you like to go next? I think there's already a good discussion because Moin and a lot of academic works have shown 10% performance overhead with PRAC, at least the current implementations. And Kuljit is claiming it's 1% to 2%. Yes. yes, I know. Okay, yeah, so we're going to hopefully resolve this disconnect today, but I'm not sure. Let's see. Okay, Salman. Your slides are already up there.
Well, I guess I can just
hold it. Yeah, that
yeah.
might be better. It's over there if you want to.
Okay, yeah.
On that computer, right?
Yeah, it's.
Is that okay?
Okay.
Someone can.
Or I can just say next slide when. So I want to start. So first, allow me to introduce myself a little bit. I sort of have an unusual background in that I don't have a PhD. And I work for a software company, Google. And nominally, I used to work for a software company until a few weeks ago. I left Google. But nominally, my role was not of a researcher, but in practice, it became the role of a researcher. And ever since the pandemic, I have been working on rowhammer. And it's been quite a nice change, and I've enjoyed it very much, and I've learned a lot. And I've worked both on the offensive side and the defensive side. So I have some unique insights because of where I've worked and whom I have worked with. And so I'm going to talk a little bit about why I think what my position is on whether PRAC is enough or not. To understand where we are, we need to understand where we were. In the DDR4 timeframe, the defenses got defeated, and they got defeated by researchers in academia who were able to reverse engineer those defenses via side channels and other mechanisms, or fuzz against those defenses and defeat those defenses. And the lesson that comes out of that is that you can have a rowhammer defense implemented in memory that people believe in and trust for a number of years, after which it gets broken, right? And this lesson is still important today in the context of PRAC. And it was also true when we were approaching PRAC. So there are clashing interests here. The large customers of memory would like their memory to be secure. They would like to have assurances about their memory. They do not want to find out tomorrow that that memory that they have deployed on millions of machines and that they cannot replace quickly is vulnerable to rowhammer with no solution in sight, right? And in DRAM mitigation implementations that are opaque are the antithesis of this. They do not want to have implementations that they don't understand present, because they cannot reason about their security, and their security will be disproven at some point in time in the future. From the memory manufacturer standpoint, it is fairly important to have their competitive advantage and trade secrets, right? They would like to have the freedom to innovate. They don't want to be told, you are going to implement X, Y, and Z exactly like this. And so you cannot actually agree on a single implementation for rowhammer solution, because actually in reality, the requirements that are only known to the manufacturer of the memory, they stem from how the memory works internally. And we, outside of that, are not privy to that information. So there is this gap here, and that needs to be covered. So desirable characteristics in a practical solution to rowhammer are that it needs to be principled. It needs to have something behind it that can be proven, argued about, discussed, and it cannot just be ad hoc. It needs to be practical. It needs to fit in the area that we have. It needs to perform the way it needs to perform, and so on. Because if it's not practical, it will not be adapted. It needs to have the correct partitioning of concerns. You don't want every SOC vendor in the universe to know the details of how every memory chip in the universe works. That cannot be the solution. And it needs to be somewhat future-proof, because you can't keep redesigning the concept every 3 months or 6 months or 1 year. Next slide, please. So PRAC is actually a framework. It's not the name of a solution to rowhammer. The specification describes the general principles and an interface. There are per row counters, and there is a back-off mechanism. There is no universal implementation of PRAC. Requirements in the DRAM are not universal. Every DRAM chip is designed separately. There may be variances from vendor to vendor. There may be variances for different parts from the same vendor. And implementation within DRAM is based on the design trade-offs of a specific chip, so that they have flexibility to optimize. And so this is actually a very, very complex problem. This summary here, count the number of activates, refresh neighbor at threshold, and alert if more time is needed, doesn't actually do justice to the real problem, right? This is a conceptual description. This is not any particular implementation of PRAC. And so the devil is in the details. Next slide, please. So what can go wrong? And my primary concern is correctness. So one thing that can go wrong is specification violations. I mean, obviously everyone's gonna do their best to guard against this, but there can be subtle misinterpretations of the intent of the specification, which result in a vulnerability. Or you could have incorrect assumptions about underlying media. So there might be incorrect assumptions about what can you actually hammer in order to cause a bit flip. How do hammers to two different rows that are next to each other interact with each other? What is the actual blast radius? Which bits are vulnerable? What are the data patterns? How does on-die ECC interact? Previously unknown disturb mechanisms. And DRAM will evolve over time. So none of this is static. There can be implementation bugs. You could have a very good design of a PRAC implementation, and it goes through all of the stages of implementation. And at the end of the day, what gets implemented may have a corner case. And you may have unforeseen security implications. There might be side channels that are resulting from the PRAC implementation, the presence of alerts and so on, that leak information in other parts of the system. So there's a lot that can go wrong. And additionally, you could have also power and performance issues, as other people have brought up here. You could have average case power and performance issues. There could be pathological and malicious issues. And this is an active area of research. There's a lot of papers that are coming out. And so my starting position is that PRAC is a good starting point for the discussion, and that it gives us a framework to start the discussion, because the shared set of assumptions is no longer that an arbitrary thing is implemented inside DRAM. There's some principle behind it. Are we missing something? Almost certainly. And can we do much better? Yes, I mean, that's why we're here.
Thank you very much, Salman. Introduction. Next, I'm going to give the stage to Jeremy from Micron. Jeremy is in the security group at Micron. You can
Product security team.
yourself.
Can you hear me okay?
Yeah.
Is it? Okay. Yeah, so being the only DRAM vendor here on the panel, I like to think I'm in the firing squad, but we'll see. I was kind of curious when thinking about what to say and what to present in terms of what is the DRAM company's perspective on PRAC or the industry itself. So I went to the Oracle of all truth, ChatGPT, and I asked it, what has Micron, Samsung, and Hynix said about PRAC? And what it returned was the least amount of information I have ever gotten from ChatGPT. It basically said nothing, right? No companies have commented. It's okay. What about Intel? What about AMD? Neither Intel nor AMD have said anything about PRAC. But what they have said is that they'll be compliant to latest JEDEC spec, and they will have AVO support. So first off, these are my opinions. They're not my company. But what that tells me, I'm going to go back to Stefan, the word skepticism. If the DRAM industry, or the industry as a whole, believed that PRAC was the be-all, end-all solution, then I would expect that all these companies would come out and they would say, this is the answer. This will solve Rowhammer. And hopefully next year we can have different discussions. But that doesn't appear to be the case, right? The industry is skeptical. And I think part of it is too, is that this, as Moen mentioned, is a massive change in the DRAM. This latest spec isn't just a DRAM specification, it's a host specification. For PRAC to work properly as expected, the host needs to also issue its commands and control things. So I'm here and my colleagues are here, and I think Samsung is here, right? Because we are looking for perhaps assurances, but maybe even a solution. How can we go back to our employers and provide a better option, or maybe even improvements or changes? Or I'll steal the words from Solomon, right? Is there the perfect implementation that we could come back and or design and help improve? So I think you're the last one. Oh, wait.
I can give it to me.
Oh, yeah, good.
Yeah, I think it's, yeah. Can you share my screen also? Do you have anything to share on this? Okay, yeah. Next up is Steve from Rambus. So Rambus has done a lot of work on memory, but they're more independent right now. So I saved them for the last, let's say.
Thanks very much.
Yeah.
So thanks, everybody. Yeah, my name's Steve Wu. So I've worked for the last 30 years at Rambus. And what's kind of interesting about our company is we sit really between the processor folks and the memory vendors. And so we get to work with both, and we kind of hear both sides of what's going on. So what I'm going to talk about today are kind of our perspectives, kind of seeing both sides. So a few things I just kind of wanted to kind of reinforce or echo from the fellow panelists and from Owen this morning is neighbor disturb issues are just getting worse. I think everybody can agree on that. And there has been this talk that maybe if we go to 3D structures, things will get better. I think things will just get different, right? The fact that neighbor disturb issues are there, process technology is getting a lot harder to get, 100% repeatability. It's going to open up kind of more channels. So there'll be something that's there. This general idea of security by obscurity, I know it's been said multiple times, it just doesn't work. But one of the reasons that makes it very, very bad is it's hard to provide any system level guarantee of where you are without really knowing what's going on under the hood. So that's the part that I think that's kind of the end result, which is problematic. There's been a lot of really good work by academia, many of the folks here. Lots of other folks have written papers and done good research. And what it's done is it's really raised a lot of awareness, and kind of more of that type of thing needs to happen. This is a great venue for starting to see some of the real issues that are going on. All right, now I'm going to start talking about, kind of what I see in prac. So, like it or not, in prac, the counters are accurate, right? So they are providing some piece of information that is accurate, presuming the counters are implemented correctly. So there is some base piece of information that you have that is accurate. The question is what you build around that. And so it's kind of an interesting building block. It also has a relatively small overhead. So if you're talking about, say, a 16-bit counter per row, something like that, it's relatively small per row in the DRAM. And if you think about the on-die ECC that's already there, it's a couple of bytes for every 128 bytes. And so that overhead is already on the order of 6%. So adding just a couple more bytes per row, very small, right? It's also nice because if you think about trying to track in, say, a memory controller or in a buffer chip, like an RCD kind of thing on a server, one of the challenges you'd face there is you might need some amount of SRAM. And so that SRAM is constantly being burning power to keep the state of the counters. With DRAM, it's a little bit nicer because you're really only kind of burning the power anytime you access that row or when you refresh that row. So there is this really interesting power scalability aspect of it. That's kind of nice. But of course, as we all know, the downside is it increases TRC. And there are other challenges associated with the management and all that. And that's kind of what we're here to talk about today. So what's actually really hard about all of this? So I think we'd all agree it'd be really easy if everybody would just agree. Just tell me everything about your DRAM device. And the controller guys would say, just tell me everything, here's everything about how we're going to mitigate. And if both sides kind of came together and told everybody everything, the problem could be a lot easier. That's sort of not how it works, right? So there are these practical business issues that cause some challenges in terms of, really trying to put together a good solution with full transparency. So those business kind of issues or the ways businesses are done, they exist for a very good reason. I don't want to make it sound like, this is, all somebody's problem, but they're all there for very good reasons. And so the issue is really, how do you work within the constraints that the industry provides? And so I'm gonna take a step back here and do two shameless plugs here. So if you want to see a little bit more about kind of what the challenges are and trying to get something to work together at the system level on both sides, from the controller to the DRAM, we're actually doing a tutorial tomorrow on DRAM. And so we're going to talk a bit about the controller side of things. We're going to talk about the DRAM, and we will talk about RowHammer and RowPress and what makes it kind of interesting. I think the other kind of shameless plug I'll do is we published a paper a couple of years ago, and our kind of starting assumption was, let's start with what the industry allows or what the industry has today and try and build something that is compatible from the industry's view. And so if you take a look at that paper, some of the questions about why we approached it the way we did, it's really because we're trying to leverage everything that the industry has already enabled and add the smallest number of things that still fit within the guidelines that the industry operates in. All right, a couple other things I was going to say is, there were some really good points about the counters being at different levels, potentially across multiple DRAMs and say a server DIMM. There's one other thing that I rarely see talked about in papers, but it's another thing that causes this to happen, is that each DRAM will repair rows differently, which means rows, different row addresses can be neighbors in different DRAMs. And that's just because if those rows are repaired, they get moved to the repair area, but the repair maps are unique to the DRAMs. And so that's another thing that makes it very hard when it comes time to clear a counter. You may be clearing the counters in one DRAM, but not in another.
I think the last thing I'm going to mention here is that, you know, if you think about how people do RAS and ECC, they often take these layered approaches. So there'll be, say, on-die ECC, for example, and then system-level ECC, where you're doing something like Reed-Solomon codes across the whole channel. It may be the case that that's warranted here as well, where certain systems may choose to layer many more types of rowhammer mitigations on top of each other because they're willing to have, you know, maybe a very, very small probability of a rowhammer attack being successful, as long as it's not repeatable across systems, right? But that may be okay as long as the trade-off on performance is acceptable. There may be other systems that require that ironclad guarantee. So I think that may be another way to think about the problem. But yeah, those are my thoughts.
Okay. Thank you very much, Steve. Okay. Boy, do you still want to talk? Okay, maybe, yeah, just keep it closer to your mouth so it's easier for others online here.
Okay, so some high-level takeaway, right? That I assume that my perspective on this is clear, right? I would take a more broader perspective. Engineering is not about putting 10 pounds in a 20-pound bag. It's really about putting 20 pounds in a 10-pound bag. We can solve the problem by having a high-cost solution. I know it's a principal solution. What concerns me is not the general framework or its security. It is a fantastic thing, right? It's probably the thing that has the highest level of security. My concern is, are the costs high and are they justified? Do I want my laptop to become 10% slower because DRAM industry did a bad job with their TRR design? Somehow everybody thought that we can't solve it with TRR. So we came up with a high cost solution and then everybody's paying 10% for it. And this 10% versus 1% disconnect is actually important, right? It's important to think about what performance means. Performance doesn't mean bandwidth. When it means latency, yes, you're going to pay high. When I talk to some of the industry people, they also say, you know, one feedback we have for you is that you assume thresholds of 500, 250. Thresholds are not that bad. In fact, they are not even 5,000. I mean, somebody found a small bad part and they said 4.8K. We don't see it. You can't take both views that my thresholds are 10,000 and I'm going to solve it with a high cost solution when it's almost trivial to solve it at 10,000 threshold, like the memory side thing that I talked about, or TRR with like really, really low cost, right? Even if you refresh once every 6 or 8 refresh, it will solve the problem, right? So there are two things. One, solving the problem at low cost, I would say at above 1K threshold. I think low-cost solutions exist unless PRAC becomes performant and lower cost. My vote would be, I don't want my laptops and machines to be unreasonably slow, 10%, for a problem that could anyways be solved, right? Now let's change the regime to second regime. We're talking about thresholds of few hundreds. I would say you should do PRAC. I don't care about performance at that point. We'll come out with creative ways to solve the problem. So it's a bifurcation, right? When you get to ultra low threshold, I don't know of any other way of solving the problem other than PRAC. My concern is that's a long runway. We should not be starting to pay high costs upfront. I love my laptop and phone to be high performant, right? When I buy something maybe from Apple, I actually want it to be 10% faster, not. So the concern is that if PRAC gets mandated, everything gets slowed down. Even if it's one time, it's basically for eternity, right? Second, rowhammer is only rowhammer. In fact, in 2021, when I had submitted a paper in response to the invite from Stefan, I'd argued that memory ECC should be architected such that you have strong detection. And my argument that time were that there are no knowns, known unknowns, and there are unknown unknowns. Failures will happen that we don't even know about because rowhammer is just the start. 2023, Onur's group comes out with RowPress, right? Rowhammer, RowPress, there will be more gremlins coming out. Let's come up with a principal solution. For example, detect heavily or invest heavily in detection code. Detection code, integrity, protection are a good mechanism to deal with integrity errors. With DDR6, I'm hoping that there is some support for extra metadata bits per line that could be used with integrity. Thank you.
Thank you, Moin. Okay, now that we've heard the opening statements of everyone, any comments, any responses to anything you've heard so far? I think Kuljit is burning to make a comment over here, so go ahead.
Yeah, thanks, Moin, for your comments. So these technologies have to stay in the market for a while. Like look at DDR4, DDR5, even DDR6, maybe there for 7 or 8 years. So you want a solution that's scalable. We can't design a solution to 1K and then the threshold is down to 100, and then you again are scrambling. So you want a solution that can scale over 7, 8 years of that technology lifetime. And PRAC was defined with vendors can control their thresholds. There are users that can also adjust the thresholds to make it more, to go to a lower value. So there are a lot of unknowns. Even memory vendors don't know what the next process node would look like, how RowHammer is going to manifest. So you need to build this insurance policy and pay that and design that upfront versus keep scrambling every couple of years and come up with a new solution. So PRAC was used to address that.
Okay.
You're actually saying that you care about 100 threshold. I want you to tell that to Stefan, because every time he reads my papers, like, why are you talking about thresholds of a few hundred? I don't like that the fact that you're writing papers with thresholds of few hundred, right? Second, if yes, no. So either this is a fight that you both should just settle. I care about 100, or you should not care about 100 at least for the next decade, right? Second, look at the slope. If you look at the slope, in fact, I've had discussions with multiple people on this panel. The thresholds have somewhat stabilized, right? We haven't seen a part that has sub 5K thresholds revealed so far, right? So I'm not saying that we shouldn't think about, but making everybody pay a decade before when we arrive is a bad idea, right? So if really that is a concern, what I would say, have two solutions. It's actually not.
It's already arrived, Moin.
Yes. So what I would say is basically the approach should not be, hey, we are just going to do PRAC, live with this 10% slowdown. It's one time, just keep paying. What I would say is that I would then urge the memory industry to have a very ultra low cost solution, for example, like Mint or possibly even DRFM, be available such that at least for the decade that we don't have to worry about sub 1,000 threshold, I don't want to pay the high cost, right? So I'm saying that, yes, there is a lot of paranoia in security solutions, and I mean, I understand that. If we are not at sub 1,000 threshold, and I don't think that in the next couple of years we are going to reach sub 1K threshold, there are solutions that are low cost. I would encourage for the next generation to next generation of DDR memories to explore. I mean, basically, there's a reason why I put that picture, throwing the baby out with the bathwater, right? In this discussion for the last half an hour, we're like, PRAC is good. PRAC, if only PRAC could be like a better child. Everything is about PRAC. The fundamental question is, we are not here. The objective should not really be how good is PRAC? Can PRAC be even better? The right question is, what is a lower cost solution? What's a practical solution, scalable solution to solve RowHammer that makes sense for the next decade, right? That is the right question to ask. I think I disagree with the framing of this panel that implicitly assumes that PRAC is the only thing that's worthy of a discussion in this panel. No, this panel is about DRAM security, right? I take a contrarian view that PRAC, mandating PRAC would actually be a wrong decision for the DRAM industry, wrong decision for Giray. PRAC as an optional feature, fantastic. If I care about security, I don't mind paying 10%, do it, right? If you force me to pay 10% for a solution, it's unclear when the sub 1,000 threshold will come. then I won't be happy. I don't know why the Apple, Samsung, Google of the world want to pay this.
Can I have it? Because now I have to respond to the framing of the panel. There are two things I will respond to, and then I'll give it to you, Salman. One is PRAC a good solution to DRAM disturbance? That's the framing of the panel. So you actually targeted the right thing. So we're actually covering PRAC. I agree that it's not a good solution, frankly. This was like when we wrote the RowHammer paper, this was the first solution that we came up, and we said that this is not even interesting to explore. But now industry went back to it. Yeah. Yeah. I'm not sure. I don't agree with that either. So I think there was also another thing that I would, so the panel's actually broader than what you said. The second thing I would like to say is, first of all, I'm not sure if we're not below sub 1,000 threads. We don't know where we are. I believe we're actually, with some of the variable read disturbance, RowPress effects, we're much below sub 1,000. So we're at that point, but that doesn't mean PRAC is a good solution for that either, in my opinion. Yeah, sure, okay. Yeah, sure. Yeah, I agree, but I don't think PRAC is a good solution even at sub 1,000. So I'll be a little bit, let's say, controversial. Stefan can defend if he wants, or do you want? Okay.
So first of all, actually, a couple of things. One is I think the audience should ask some questions. Okay.
But I want to exploit this heat right now.
I like his framework that PRAC is actually giving you a framework on how to actually implement. From my perspective, when actually I was pushing a JDEC to implement PRAC, to me, the way you track things and what you do, I kind of, sort of, I'm okay with trackers, per row counters, whatever it is, as long as if the DRAM needs time to actually go mitigate something, raise alert, don't flip bits. So to me, the nice thing about designing this as a framework is that it lets the DRAM vendors innovate into how to actually keep track of the problem, and it's up to them. Two, another point, I spent quite a bit of time designing a memory controller solution for RowHammer, and at the end of that process, I realized that the memory controller is the wrong place to actually solve RowHammer. Because after spending a whole bunch of time working on that, we realized that actually some DRAM parts come with folded bit lines, and that completely changes your design. And we're like, oh, we had no idea this happens actually. And there was a third thing I wanted to say that I forgot now. Oh, one other thing about the threshold. One thing that I haven't heard speaking about, this gives you a framework to go innovate, is to consider per row thresholds. Now that we actually add a few bits to implement a counter, maybe we can add a few bits to actually also store a threshold. And that might actually give us some runway. It's an interesting idea, I think. You there was a question in the back.
Prashant, come ahead.
Is it like a urgent question? Okay, is it going to continue this discussion? Because I think Salman has something to say. Okay, but before Salman goes, I would encourage Stefan to submit his paper Yeah. Okay, I know I was conflicted with the paper, but I think it shouldn't have gotten rejected. Yeah. Okay, yeah, maybe, or maybe it wasn't hot enough of a topic for the, okay, whatever. Yeah, okay, yeah, okay, please.
So I have 2 points. One is that earlier Moin was talking about how he is okay with Prag being an optional feature, but he's not okay with Prag being a mandatory feature. And even before that, he said something which is contradicting this position, which is that, below a sub 1,000 threshold, Prag makes sense. So the missing piece of information here actually is like in DDR's whatever time frame when Prag becomes mandatory, what will the thresholds be? And that brings me to my next point, which is that RowHammer thresholds are actually not as simple to figure out as we all think. And there are unknowns there in terms of like, well, RowPress was an unknown, for example, and there might be other things in terms of half-double type effects that involve interaction of multiple rows and so on. So there is a risk there that we don't understand row hammer thresholds very well. And we should look at that also in light of like introduction of new features in DRAM, such as on-die ECC and how and you know, interaction of data patterns with row hammer threshold. There is a lot of space to explore there, and we can have uncertainty about row hammer thresholds, which is actually a fairly dangerous thing to deal with if we're gonna assume that, you know, above or below certain row hammer threshold, certain solutions make or don't make sense. It would be really nice if we got some audience questions.
Given our time check, let me
30 seconds. 30 seconds, okay.
So we're conflating two things here, right? I would say that if you give me a 10% budget, you can solve row hammer with TRR and host side till about 250 threshold, right? Like so it depends on how much budget you're willing to spend. Second, these things can be configurable. Third, the not knowing the threshold and not knowing what new modalities come, PRAC doesn't automatically absolve you from that. PRAC also requires configuration parameters. PRAC also requires that you be aware of RowPress. So somehow it has become that, look, solutions X and Y, but then I have this PRAC that will just solve automatically everything. No, though that applies to everything, right?
Okay,
Yeah.
thank you, Moin. So, okay, now audience questions. Who wants to come? I see. Okay, Prashant yielded. Do you want to come here? Please line up. Go ahead. Who else? Feel free to line up over here. And ask the tough questions, please. Yeah, go ahead. Oh, you can use this mic also. Yeah. Cool.
Thanks, panelists. I'm Adi from ETH Zürich ComSec. One more serious concern that I have is that let's say we have like a perfect implementation of PRAC, it's configured perfectly, right? But the problem is that even what Jeremy said, what the CPU vendors would do, right? Right now we have like a recent publication using security that we showed that CPUs do not even issue RFMs, right? So we have these DRAM DIMMs that they have RFM values advertised, but no signs of RFM issued by the CPU. So even if we have PRAC and we have these reactive mitigations, would you trust CPU vendors to actually give you this additional time? And maybe after maybe a TR or Mint would be a better option.
Who wants to take it? Okay, let's comment.
Here's an observation that I made, which is with PRAC, actually, the DRAM vendors have done the heavy lifting of actually implementing that in DRAM parts. And we all know that's a lot of work, biggest change to DRAM in 20 years, The SOC vendors have not done even an okay job of making alert less expensive than it is. They seem to me unwilling to do that. And because alert is so expensive, there is all this hesitance to actually, maybe we should never, or we should not, or we should be judicious about how we raise alert. So if there's a way to actually keep the SOC vendors more accountable to make their alert, I don't understand why alert has to be so blunt of a mechanism and why cannot be made a little bit more lightweight.
Kuljit had something. Go ahead.
Yeah.
There's a SOC vendor over here.
First, to address the RFM, so it depends on the vendor implementation. So some vendors will say RFM not, so even if you issue an RFM, it may not get used. So it all depends on the DRAM internal implementation of whether they need RFM or not. Well, then talk to the CPU vendor. Yeah. Yes, but the CPU needs to follow the DRAM spec if RFM is required. So yes. And the alert is also part of the problem on alert is it's a heavyweight because alert there's a CRC errors on the DQ bus, there's CF parity error, there's a lot of things piggybacked on a common signal. And it's also shared across multiple ranks, multiple channels, so it becomes a heavy lifting to address alert, but there are ways that it's getting more optimized now. So down the line, they're also investigating a sideband to a DRAM where you may not need alert, you can get information ahead of time. So other options are being explored to not yank on alert because because you need to replay commands, it's a very heavy lift on the system side.
Take point.
I know I've been bashing PRAC the whole day. Let me give compliment to the DRAM, whoever came up with the spec on ABO. ABO is fantastic. The difference between the threshold of Mint versus just PRAC without ABO is 2x, not that much. Like PRAC by itself is actually not that useful. But it's ABO that makes PRAC shine. Right? So fantastic job. That's like a very creative piece of signal. The right question to ask is not PRAC plus ABO versus Mint, right? The right comparison is PRAC plus ABO versus Mint plus ABO. Go implement ABO, go implement alert. It is something that can be creatively used by randomized trackers. It is not something that should be just for counter-based trackers, right? So again, my concerns tend to be that PRAC, oh look, PRAC plus ABO is so good. It's not as, other thing is not, but whatever you added to PRAC, also give it there, right? In fact, once you give it there, maybe you don't need to spend that much time in refresh. Maybe you can come up with very intelligent solutions that get time as needed, right? So that would be my response.
Okay, I think I'll make a comment over here also because I think this is an example of I really appreciate the fact that people are solving the problem and looking at solutions like PRAC, but this alert, the abusing of alert, I would say, is an example of the DRAM industry not wanting to change at all. And I think there are much better interfaces that we can design that can enable the DRAM to do much better internally, but it changes the interface, so people need to agree on it. Like we've been trying to push for the self-managing DRAM work that was published after 6 rejections by academic folks plus industry folks at Micro 2024, which is a more, let's say, generalized interface that can enable some of these solutions in a much, much better way. And DRAM vendors can be actually have a breathing room to solve the problem in an easier way. But it doesn't solve the problem of security by obscurity, which I would like to get into at some point, maybe, but let's see. Okay.
Yeah, so I have a problem with the panel. One of the issues that I did not hear anyone speak about was the fact that software needs to be aware of PRAC, right? There could be cases wherein you have physical rows being shared by different pages. You can have pages that are mapped separately, right? Differently. And do you want to live in a world where one user can influence another user via PRAC? I know it's sort of a black box design, but I think that's something that we should consider. Another question, or more of a comment, is that security is a worst case study. When we're talking about thresholds of 200 or 300, I'm assuming that's the 99.99 percentile, and the average is somewhere at 5,000, 4,000, right? If you assume the average to be 100, then the 99.99 percentile is 1, right? So I think that this is coming back to what Stefan was mentioning, right? So if you're having counters that sort of ride the wave, the bell curve, that's all good. But we should sort of at least think of PRAC in a more secure sort of manner. Right? So that's it's not a question, but that was a comment. But the first one was a question. So thanks.
Okay. Anybody wants to take the question?
I can quickly take the question.
Okay.
So Prashant, I think there are 2 parts, right? One is the side channel work that is getting presented. I really love that stuff, right? And it's funny how 4 academic groups within 6 months of each other were all working on the same thing. There's a similar paper coming up at Usenext. I know Onur's group has been working on it. My group was working on RFM-based side channels. When we develop solutions, it's important to think about the security implications. I agree with you, right? Second, the performance aspect of one's access is contending with the other. For RowHammer, at least a threshold of like 500 or above, I don't think that's really the pressing problem in terms of contention. Yeah. So okay, but sometimes, like for example, this out of sync counters, right? So let's say if your threshold is 1,000, if you have 4 chips, basically in the worst case, you're sending an activate every 250 or alert every 250 activations. That's a performance overhead of sub 10%. Currently, the cloud vendors actually don't do bank partitioning. They allow accesses of one application to contend with others. That is like a 50%, 2x slowdown worth of scope. In that regime, it doesn't make sense to think about what might cost 10% slowdown in the worst case patterns. It's so the differentiating concern. Side channel, important. Minor amount of contention for worst case pattern, not particularly important.
Anybody else wants to take the question? Okay. Other questions? Oh, there's one back there. Okay, cool. Okay, there are two. Okay, even better. You can use this one also. So.
I guess my question is to Stefan. Oh yes, I'm Ritvik. I'm Moin's student. This is Moin's ex-student. Yeah. So when you said there config, like this has been like a constant topic here. What are the configurations of PRAC needs to be configured correctly? One of the things that I can think of is multiple PRAC counters being in one row, and then you attack the PRAC counters themselves. Like, okay, what are the configurations then? When you say the configurations can be wrong or it needs to be configured correctly, like, can you mind shedding some light into that?
So yes, thank you for your question, and thank you for thinking about this. So so let me phrase it this as a problem. The host actually, so you know, cloud providers actually do have incentive to make sure they don't have ROHAM. The thresholds are now configured by the DRAM vendors, and they're completely invisible to anybody else. The host will like to actually adjust those thresholds. And there was a little bit of a tussle there where given by the fact that the DRAM vendors are really paranoid about providing any sort of transparency to the threshold. So where we settled there was that the host can say, oh, please reduce your thresholds by 10%. So maybe there is which is kind of like, I don't even know what that means. From a host, I don't know, what's 10% of 10,000, of 100? What's 10%? So there might be an interesting design to think about something where you can actually give some control of the threshold in a way that maybe provides some sort of protection to this paranoia of the DRAM vendors not having to reveal their thresholds. I'm not sure. I don't know what the right solution is, but something like that. It's a hard problem. I can't think of a way to do this. Yeah, that's, you know, thresholds are definitely an important parameter, but pick up the DDR5 PRAC spec and look at every single parameter there. And, you know, that is actually not being explained who sets it and what sets it. I actually have an article on my website as well. So all of those, if they're set wrong, then it won't work. So maybe is there a way to prevent that or protect that in some way that, again, goes with this requirement that the DRAM vendors have, which is we don't want to tell the world anything about these thresholds.
Would that be a performance versus threshold trade-off that we would be providing for you? Okay.
So there is a performance trade-off, but if the host decides to change the threshold, then it's, you know, the host make that decision in exchange for the performance. I would like to have a lot more control over the thresholds than I have today for future. Okay, great. Okay.
So the couple of knobs that are in there, I think one is on the bank activation threshold. That's for the controller to observe, and other is a number of RFMs you want to set it up for. So one is if you want, in some systems, there's a real-time traffic or the ISOC traffic that's very important. So you don't want to, so for those systems, RFM of 1 was defined. So we can go back and get back to the display traffic, and in some systems that's more critical. In some data centers, once you're in this mode, might as well issue more RFMs and take care of more rows so you're not in and out that often. So there was a debate on managing ISOC traffic versus trying to mitigate more once you actually alert is asserted. So that was one of the knobs to play with. Other was the bank activation threshold. So that reduces the probability of alert. So you can have a bat of a low where you can doing a lot more RFMs, wasting performance and power. I think and in that case, you may never see alert, or you can have a system where you say, I'm not gonna follow the bat spec, bat is optional. Maybe you never see alert, and that gives you a knob to say, I'm not seeing alerts, I didn't issue any RFMs, and there are no bit flips. So in that case, so you can play with the bat knob, and if you're getting more alerts, you can go change your controller thresholds. So there are different ways to work around some of those knobs provided in the spec.
So I was having a notion about bat.
Okay.
Bat doesn't make sense at all.
Okay.
Let me explain why, right?
And then we'll go to over here. There are other
Let's say, no. This is a point of contention. Alert stalls per the spec stalls the memory for 350 nanosecond. If you don't want that to happen, you can proactively stall the memory for 350 nanosecond. That doesn't make any sense. So if your car crash is insured for $1,000 and you don't want to pay that $1,000, so every month you pay me a premium for $1,000. I mean, that doesn't make any sense, right? So bat spec under alert doesn't make any sense. And this is something that I've told Salman also. It doesn't make sense to proactively keep stalling for 350 nanosecond every N activations in the hope that you can save 350 nanosecond.
Steve,
Yeah.
Steve, let's Steve go.
Yeah, so a couple things I wanted to mention were, you know, the DRAM spec is really kind of a contract that says, okay, the DRAM manufacturers guarantee that if you do these things, the DRAM device is going to behave a certain way. But the issue that comes up a lot is, you know, when the system guy uses the DRAM, the system guy assumes the responsibility of providing the performance and reliability levels that they have decided are right for their customers. And that's where a lot of this kind of challenge comes in. So I'll give you just a couple of examples. Most memory controllers can adjust their refresh rate. And it would be helpful to know what the impact of changing the refresh rate is on the probability of rowhammer being successful. And you should need to know the thresholds, but that isn't communicated, right? Another example is, we talked about refresh back off, where you can delay some number of refreshes. Most controllers can actually adjust the number of refreshes that they're willing to back off. It's yet another way to kind of adjust the performance versus reliability. So a lot of this is kind of the difficulty or the way that the industry and the businesses work. And that's this complication that I see in rowhammer and RowPress, where the business issues start to actually kind of influence what the industry needs to do.
Very, very well said.
Thank you.
Yeah.
It is not just business issues, but it's also the fact that I guess it is sort of a business issue if you think about it this way. But basically, if I put myself into the shoes of a memory manufacturer, I want to agree to the specification and not one implicit line more, right? Because I don't want implicit assumptions on the behavior of my product that I have not agreed to in the specification, because they take away my flexibility to innovate on my product. And that gets very tricky because, let's say that you make some assumptions about postponement of refreshes and their effect on rowhammer mitigation. And, in one die revision, it's working, and in the next die revision, the attack goes through. It creates a very uncomfortable situation, right? Like you're violating a contract because it worked in the past that way. And I think that's not actually reasonable.
Can you comment on the overhead of alert? He was talking about if alert is so cheap, why do you worry?
No. So alert is very disruptive at a system level. A lot of systems don't want to get into that mode. I mean, some controllers are more complex, can handle that. So you have to stall traffic, clean pipes, and so some systems can handle that, some cannot. So a lot of the systems are willing to pay this extra overhead or the insurance, so they never get into a situation where they're trying to go and stall traffic and stop the pipelines and then and go. Yeah. So. Yeah. Yeah.
Say, good, I now don't have to implement.
So- Yes. Right. Yeah.
Then the matter how long of a stall I have. And if that stall is the same as that stall anyway,
Yeah.
of performance, it doesn't really change it. And where the stall can come in, JEDEC can actually specify, right? Remember the diagram that I showed after the insertion of alert, 180 nanosecond of regular activity, 350 nanosecond of stall. It doesn't matter. I mean, as Salman said, I am just looking at the spec. That spec says that you are going to be stalled for 350 nanoseconds. If JEDEC doesn't believe that to be true, it should not define it that.
Yeah. So. Yeah.
Bank versus all banks is not a problem. In a currently bank system where all banks have something to mitigate, all bank solutions are same banks.
It's a very long discussion. So if we can continue a discussion and then go to the questions. Yeah.
Okay. Okay, Guraj, go ahead. Take this also. So we're running out of time, so you're allowed to be very quick in questions then.
Guru Raj from University of Toronto. So I'm going to shift the topic a little bit to slightly higher level. So I think all of us agree that security by obscurity is a terrible idea, right? And that kind of echoed in multiple presentations. So I really like PRAC because it's a spec. It allows us to speak in the common language, between different industry partners, between industry and academia, etc. But we, I think, also agree that devil lies in the details, right? Like implementations really are going to dictate the security, not the spec. So what should we be doing to avoid a scenario 5 years later where we discover that maybe a particular implementation is not secure, right? Academia can definitely put out designs, and we're already doing that, but what should be some things that industry potentially does in this scenario?
Okay, thank you. Salman, okay, I was going to put a DRAM manufacturer on the spot, but Salman go first, and that'll give time for Jeremy to prepare.
So I have a sort of a straw man suggestion for what could be potentially done. And the memory manufacturer can take their implementation that they intend to implement, remove from it aspects of it that they feel are sensitive, and basically publish that as a simulation model out to the world and say that this is how we intend to roughly implement PRAC, and people can try to break it. And the earlier you do that, the better it will be.
So that can't.
Yeah. Jeremy, please.
If we were going to do that, we would have done that. No, I think that the short answer is, and I'm going to go and echo what Moen said this year and last year, which is provide a solution. Come talk to us. I mean, at least my group is more than happy to take your ideas and bring it into the company, right? And I'm hoping my counterpart, Samsung, will have the same viewpoint.
So I have a question for you based on that response, which is like, how do we know we're doing the right thing and not wasting our time? Because if we don't understand your problem statement, the solutions we are working on can be completely useless.
Yeah, agreed. And this has to be, unfortunately, going back and forth. Like I said, if the DRAM companies were going to open up and tell you everything, they would have done it. Sure. Oh, you want this way? Yes.
I wanted to say one other thing, which is it's obviously a very chicken and egg kind of thing. I've talked about how the DRAM manufacturers, that spec is the contract. The thing that I've often felt would be nice is if there was some commonality among the systems companies where they could define some framework that they're all willing to operate in, or at least a majority of them are willing to operate in, because the DRAM spec forms that on the DRAM side. So I think if you had, if you had that on both sides, you might be able to at least match the two a bit better and really kind of understand, okay, these solutions provide the flexibility for these particular system needs, and these other building blocks provide the flexibility for these other needs. So it's a lot to ask for, but I often wish that there was some more common framework on the system side.
Yeah, agreed. And where is Intel and AMD?
That's a good question. They have other troubles. Well, yeah, Intel at least, yeah. Yeah.
Okay. One thing that should be done, and CPU vendors do this nowadays, right? There's a way to send a hardware patch to reconfigure CPUs. It's good for DRAM vendors to actually think about hardware patching frameworks such that while in the field something happens, you should have ability to sort of modify things, right? No, remember, this is for your own good. The Intel and AMD did not do this out of their what?
Okay.
Intel had FDev bug. That's where hardware patching came in, right?
Okay, I'm going to move to Irina quickly. We're already out of time, so please.
Quick question for Jeremy, and taking cues from everything that was discussed today, but slightly off the topic. You're implementing PRAC and all these solutions. Why are you not looking at stronger detection code that actually solves a lot of these problems, right? We are still stuck. I am talking from an LP perspective. We are still stuck at 136, 128 sec code, which has terrible, even double error detection. So why not push for a stronger detection that might have a better future, right? So.
I think the biggest challenge is that DRAM is a commodity component, and I'll speak at a very high level here. And we don't have a lot of area, to be perfectly frank, right? I mean, that is true because, yes, exactly. Driven by a spec, we are implementing PRAC. Exactly. So I think as everyone's aware here, right? If there was a JEDEC spec that says we need to use an error correction code as opposed to PRAC to solve it, and all the DRAM vendors went and did that, right? Because we're forced by the spec, and that changes the conversation. And that goes back to the business discussion.
Making companies to agree, right? And
yeah.
If Apple wants solutions that makes their system so well, come on with it.
Yeah. Yeah, that also, I think, shows how broken our memory processor interface is, as you can see, right? It's so broken that you cannot change things easily. I think, aside from the conference reviewers, memory interface is one of the things that limits innovation greatly in our systems. Okay, yeah, last question I'm going to take from you. Introduce yourself.
Okay,
Okay,
it's going to be fair enough. Hey, Jeremy. So I work at Micron with Jeremy. And I have largely a question for the DRAM, like the system integrators. How I kind of see this on Moen's point is you kind of have this chicken and the egg problem where if I'm a system integrator, I want to do something with, I don't like some of the specs, but you want to do something to help with RowHammer, but at the same time, you expose yourself to a degree of risk. So you you have variable timing delays, and that can kind of expose your solutions like confidential computing. So it's easy to build side channels off of something that has a data dependency lag. So there's that problem. And then there's the second problem of I kind of just want to trust the DRAM providers and not have to do that, but I have to trust you in order to kind of do that. So it's kind of like this really also expose yourself. And do you think you can give, particularly for things like confidential computing, do you think you can maintain that promise while at the same time preventing, RowHammer issues, particularly when you have this data dependency problem introduced with PRAC and RFM? Like, are you sacrificing something by not trusting the DRAM providers? And if the DRAM providers were able to build trust, would you be more inclined to not, have RFM or some of these PRAC level system controls that increase this backoff problem and expose things like confidential compute, which you own? So that's kind of my question, is how do you balance that dichotomy?
Okay, thank you. Quick answers. Who wants to go? Okay.
Answer to your first question. The reason why, so Microsoft has a multi-billion-dollar industry on top of cloud computing. And if cloud computing were to be actually, and the concern is nation state attack, not people with a lot of free time on their hands, but people who are smart and have a lot of budgets and they want. So one of the things actually I want to say is that cloud providers have not yet heard the messages that they need to understand how to run their infrastructure in times of conflict. We've never done that, and it's coming. And in those times, it'd be nice to have some sort of control to basically say, we're going to trade off a huge amount of performance in exchange of actually making some forward progress under strong guarantees. I didn't answer your confidential compute question, but I'll be happy to talk to you about confidential compute too.
We have a lot of time after this. Any other takers? Steve? No? Okay. No, you're going to go past. So let's take the online question then. Anybody wants to read the question, because I don't have access to it right now. If you can make that bigger. Okay, I'm going to try to read it. Question to all panelists. Stefan's point on correct configuration is really important, and the solution relies on testing chips. However, we still do not have a good testing infrastructure for DDR5. How can we solve this issue? Does your respective company have any plan to support such testing infrastructures in future? This is from Giray, who did his PhD thesis on this topic, and he did a lot of work. Who wants to take this? DDR5 infrastructure, getting data.
DRAM testing would have entertained that, but for the kind of work that.
Yeah. Sure. That doesn't answer the question, but yeah, that basically says we need the infrastructure more and more to keep the DRAM industry and the industry in general honest, let's say, but okay.
Very quick comment. Actually, I don't think DDR5 is I agree with the question very much. We don't have the right tools to actually look at DDR5. DDR5 is just the tip of the iceberg. We don't have the tools to look at HBM, and those tools are really, really hard. And the amount of money that we are betting on HBM working correctly is immense. So sorry for my.
Sure, no problem. I agree. I think I definitely agree. Yeah, HBM. Yeah. Okay. Okay, Jeremy. Here. Yeah.
Yes. Yeah.
On the panel,
yeah, I know. I think at this point, as brought up, yeah, there really isn't a research opportunity for DDR5. As you mentioned, HBM, right? These are, especially HBM in particular, is a very, very expensive technology. And not only that, but once you put that HBM stack on, it ain't moving. It's not like you can probe pins. So you're talking about a very, very different architecture. And I think this is something, maybe that the research community along with the industry can come up with, I don't know, an open source plan about how to actually tackle this. But yeah.
So just to be clear, in the RCD spec actually has some provisions to actually test DDR5, and I know Future Plus Technologies is actually taking advantage of those. So you should look into that. Of basically being able to interpose at a level. The idea is to actually have, for DDR5, is to have an interposer with an RCD. So the interposer itself has an RCD, which then actually goes back to single data rate speed. So you interpose behind your RCD, and there is a way to have two RCDs on the channel. There is provisions in the spec to do that. What's the point of this? Maybe there's an opportunity to think about how to design a protocol that allows you to actually build interposer and testers. So again, great research problems, I think.
At lower cost.
Lower cost. I think the problem is not just those, but if you want to build a controller that can test a lot of parameters, you really need something programmable. And that programmability requires support from FPGA vendors, potentially, or you need to build some sort of memory controller yourself. And that's not that easy in academia in general. And industry doesn't want to help in general. And this is true for the general industry, not just DRAM manufacturers, I should say. The general industry doesn't want to open up their memory controllers. Yeah, I'm not just looking at you. Yeah. I love industry, but I can also criticize you guys. Okay, I think we're woefully out of time, but the good thing is we have had a lot of discussions, and we would like to continue these discussions. I actually had a bunch of other questions over here. You can see some of them online. This could be some of the things that could be used for the rest of the day. I'm very actually concerned about number 3 over here. Everything like, do we have the right interface? Is PRAC killing other solutions? And I believe that there's something that's happening right now. Hopefully not. I think we need more creativity in this area, and the fact that something is standardized should not stop people from working on much better solutions. I'll probably stop at that, but it'd be great to continue this discussion. Right now we have a only 15-minute coffee break, and then we're going to have a very fast session of 7 papers presented, and then we're going to conclude. Well, that's the downside of inviting me as a program chair. You knew that it would be high bandwidth, right? We're higher bandwidth than high bandwidth memory. Okay, so please take your break. Thank you for the panelists. I think we should give them a applause. We'll be back at 11:30. I think there's coffee, but I don't know where. Steve is the master who would know where the coffee is. Oh, okay. Oh, okay. 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 Thank you, Jeremy. Yeah, thanks for taking up the panel. Yeah.
No, it's
good. Yeah, it's wonderful.
I'll inspire my Samsung.
Yeah, hopefully. I mean, I don't know. I invited all of them to the program committee also. And yeah, it's good that Micron is at least more open to talking, even though you may not give out information.
Hey, you can't always get what you want, Onur.
You must straighten up, line up.
Yeah. Are you joining dinner also?
Yeah.
I sent the location to the program committee. I can send it again, but yeah, if anybody else like Tamara wants to join dinner.
Yeah, let me ask.
She's more than welcome to also. I don't know the other Micron person. So.
Oh, holy.
Okay. Yeah, feel free to include. I think we have space.
Okay, absolutely.
Yeah.
That'd be great. So,
Sure. And I'd like to prioritize people who are like contributing to the discussion.
Absolutely. No, we're trying.
Thanks.
Let me just drop this.
Okay, it's here. All right, there. You can mute some. Okay. This was a short break, I understand, but you'll have other opportunities to discuss. We're going to start our session. We have 7 papers. This is the most we have had at DRAMSec. I think some of you guys can discuss during dinner. So we've ordered the papers in some randomized order. We're going to first start with Sudoku, decomposing DRAM address mapping into component functions, and Minbok from Seoul National University is going to present the paper. And this is going to be a pretty tight schedule, 10-minute presentation, at most 3-minute questions. I'm going to cut off the presentations, which is not my style, but let's see. Okay, you want to switch to Minbok? And you can put it. Oh, I need. Okay.
Yeah, okay, let me start my presentation. Yeah, I'm Minbogi from Seoul National University, and today I present, yeah. Yeah, today I'll present our paper, Sudoku decomposing DRAM address mapping into component functions. Okay. Yeah, I skip. Yeah, modern DRAM-based memory systems have become very complex. For example, DRAM-based memory system consists of multiple components, and here we refer to each structure elements of the memory hierarchy, such as memory channel, length, DIMMs, bank groups, and some other components as DRAM components. And also to map physical addresses to DRAM location, modern memory controllers use multiple hash functions. For example, XOR-based hash functions, and each function targets a specific component. So to accurately analyze DRAM behavior, knowing component level function is somewhat very important. For example, recent low-hammer attack exploit DRAM internal structures and their internal operations. For example, trespass use refresh synchronization to bypass auto refresh and target low refresh like things. And also sledgehammer hammers multiple bank in parallel to increase their low hammer induced bit flip ratio. And also recently, precise DRAM address mappings are essential for generating memory access pattern in recent low hammer fudgers. However, to the best of our knowledge, the problem is that there is no software-based tool for finding DRAM component functions. There are existing tools, but they only focus on finding bank addressing functions, and other existing tools require physical access to the system. So to address this, we developed Sudoku, a latency-based, software-based tool for decomposing DRAM addressing function into DRAM component level functions. The fundamental of Sudoku is a latency-based timing analysis of elaborately generated memory access patterns. So Sudoku mainly consists of 2 parts, and first part is that finding the full DRAM address mapping systems to make the memory access patterns, and second part is the timing analysis based on which is the most important part of our Sudoku. So for latency-based timing analysis in modern DRAM-based memory system, we mainly focused on 2 DRAM internal operations. First is refresh operation, and second one is the consecutive memory access latency, which consists of just multiple read requests. So first is the DRAM refresh operations. As you know, memory controller periodically issues refresh commands, and the JEDEC standard defines TREFI, which defines the average interval between 2 refresh operations, and TRFC, which is the timing parameter that defines how much it will store the memory request for a certain time. And TRFC defines the time take to refresh a group of rows and known as a refresh group. So from these refresh These refreshes cause latency spikes. So we can, by measuring the memory access timing, we can just observe that the latency spikes periodically like this figure. And our key idea is that we can infer refresh groups through just measuring the refresh intervals. So for this, we generate two random memory addresses and measure their access latency. So in our tested platform, there are only two cases. The first one is that the measured refresh interval is equals to the TREFI, which means that both two addresses receive the same refresh command. And the second one is that the measured refresh interval is less than TREFI. And we assume that this comes from that those two memory addresses receive the interrupt refresh command. So here, this figure demonstrates that in our one of our tested platform, we just access two memory addresses and measure their access latency time, and there might be there was a periodic latency spikes. But when we consider a certain two memory addresses, then their peaks are exist twice as much compared to the other one. So we just assume that there might be that kind of, in that kind of manner, we can just figure out that those two addresses are mapped to the same refresh group or not. So the next one is that we just utilize the consecutive memory accesses. Since the introduction of bank group, DRAM requires different minimum timings between the DRAM column comments. And JEDEC defines this timing as a TCCD, but from the system perspective, there are timing parameters in Intel and both Intel and AMD processor called TRD, RD timing parameters. And these timing constraints is varied by their target DRAM components. For example, different channels, consecutive memory access to the different channels are quite less, demonstrate less latency compared to the two consecutive read requests among the two different lengths or DIMMs. So however, but this is the figure from one of our tested platform, and the problem is that their difference is quite very few. It's just typically just a few nanoseconds in our cases. So what we propose is to amplify those small timing differences we use to alternating those two memory streams to amplify those small timing differences. And we define that each memory stream consists of read requests that incur low buffer hit. So by alternately accessing those two memory streams, we can amplify the small timing differences of those consecutive memory accesses. So the big figure here shows the consecutive memory access latency distribution for each DRAM addressing functions. For these experiments, first we just select one DRAM addressing function among the known DRAM addressing functions, and where I generate the two memory addresses stream that only output a different hash output from those chosen function. By doing so, we can generate two memory streams that one is allocated to the one component and the other one is mapped to the other component. And these mappings are kind of determined by those selected DRAM addressing functions. So then we measure their average access latency, and we found that we can infer by clustering their latency distribution, their latency distribution is somewhat equals to the theoretical timing differences. So as in this figure, we can figure out which function is mapped to the which DRAM component. So here is the overview of our proposed tool Sudoku, and it mainly consists of 3 phases. First one is the identifying row and column bits, and it's just one of the extension of the DRAMDIC paper. And the second one is to verify the derived DRAM addressing function and row and column bits. We just checking the system's injectivity. And the last one is based on our timing analysis. We decompose the DRAM addressing function using both refresh intervals and consecutive memory accesses. So here is the result. We evaluated our Sudoku on recent Intel Core 12th and 14th generation processor called Elder Lake and Raptor Lake refresh processor with DDR4 and DDR5 memory. And we validated our results against prior and concurrent works that utilized physical probing method. And we just treat these results as the ground truth to evaluate our tool. But it is noteworthy that DRAM timing parameter is somewhat very dependent on system configuration and system's memory configuration. So if we tune the system DRAM timing parameters, then Sudoku cannot work very well. But from our tested platform, we can find that Sudoku works well. So here is one of the results of our tool. And for Intel Alder Lake processor with DDR4 memory, we observed that reduced refresh intervals for only channel and dim rank function. Here, we cannot distinguish dim function and length function because their timing consecutive memory access times are somewhat very similar. And they both receive the same refresh command, so we cannot distinguish those two functions. And the trend of the consecutive access latency order is somewhat like this. And by combining those measuring refresh intervals and consecutive access latency, we can find that we can decompose all the DRAM addressing function except for dim and length functions. And this one is for the experimental result in Intel Core processor, which is 14th generation called Raptor Lake refresh with DDR5 memory. And also we checked that both DRAM addressing function are same for the Intel Raptor Lake refresh processor and Intel Alder Lake processors. And they both use the DDR5 memory. And in this case, we observed that only for the channel and sub-channel and bank orders function, we observed the reduced refresh intervals, which implicitly meaning that they use some kind of different refresh operations compared to the processor that utilize DDR4 memory. And for the consecutive access latency, the order is somewhat in increasing order. Their trend is somewhat like this. And one of the interesting point is that among the two bank orders function, because each bank group contains 4 banks, only we observed only one bank orders functions exhibit the reduced refresh intervals. And also in the case of the Intel Core processor with DDR4 memory, combining reduced refresh intervals and consecutive access memory accesses, we can distinguish these channel sub-channels and dim ranks, bank group and bank orders function. And like the Intel Core Alder Lake processor, we cannot distinguish between channel and sub-channel and dim and rank functions because their characteristic is somewhat similar. And we also evaluated Sudoku on AMD processors. So unlike Intel, sub-channel and dim rank functions show reduced refresh intervals and their consecutive access latency order is somewhat very similar. So here is the last slide. So yeah, we perform a latency-based timing analysis on real machine system. And the last one is the important part that we open source our code in GitHub so everyone can try and to use on their system. Thank you for listening.
Question? Good speaker? Any question? Yes, you want to come?
So my experience is that these timing-based mechanisms start like being not reliable as machines evolve and become more complex. Right?
Yes, right. Actually, what I thought is that this direction is somewhat very good because recently many Intel laptop system, they integrate their LPDDR memory into their system. So by using just the physical probing method, we cannot directly hook the electrical signal in that kind of system. So this can be one good option for finding some component level function or DRAM addressing function in the recent laptop system or some other computer system, I think.
Let's thank the speaker again. We're going to move to, and it's great that you open source your code. I think we need a lot more of that going into the future. Okay, our next speaker is going to be online. Shilin, can you hear us?
Yes, I can. How about you? Can you hear me?
I don't know if we can hear Shilin.
Can you hear me? I turn on microphone.
Hello?
Hello, I can hear you.
Okay.
Yeah.
Maybe I should do it here. Shilin, can you speak?
Yeah.
Okay.
Is it okay?
Okay. I think you're good. Are you going to present?
Yeah, I will present.
Okay. So are you sharing your screen?
I have just shared.
Well, we don't see it.
It shows on Zoom that it's shared.
Okay, thanks. Yeah, thanks for joining us. What I'm going to do. Can we do this? Okay. New better one. Can you speak again?
Yes. This is Shilin.
Can you guys hear? Okay, so you can go ahead. You have 10 minutes, Shilin.
Okay, thank you. Yeah, thank you for allowing me to present online. I have some other things scheduled during this time. And this work is called Counterpoint, is utilizing one-hot counting for Prague-based rowhammer mitigations. This is a work, joint work with two researchers, Jang-Hoon Wu and Prashant Nair from University of British Columbia. And the motivation of this work is that timing changes to Prague implementation on DRAM is somewhat hard to accept, both because the complexity of the changes that need to be made on the memory controller side, and then the timing impacts on performance when Prague actually is implemented on DRAM. So this is somewhat hard barriers to go over because the cost and then performance, both cost and performance impact. The cost is just, it's more than just the bits, also the cost of complexity as we see it. So this is a motivation slide saying that if you normalize the impact of performance with Prague, if there's no timing impacts and you will have certain performance, but for, with this current Prague implementations as is specified in JEDEC, and there will be some performance hits, and depending on the workload, high, medium, or low, you will have various different performance impacts. So the solution or the proposal we have is to try to avoid remodify, right? So this is one of the reasons that the timing for Prague implementation is longer, because you have to read these bits, extra bits, the contents of the bits, and then go through because the sense amplifier area is kind of limited. You have to read these bits out, contents out, the counter bits out into an area where you can do the counter, the addition implementations. After the implementation, then you have to write back the new content or the new counter values. So we like to look at maybe other means to implement counting without the addition or implementing countings within the local sense amplifier area. So the thing we thought about is doing this one hot counting. We know that one hot encoding only requires shifting. You start up with one of the bits that is 1, and then you shift the contents one way or the other. And the disadvantage of this is that in order to count a large number, and then the area overhead, the bit overheads will be linear instead of a log. Usually counting is a log, the counter bit's log. So one way to improve small improvement is to extend this counting by allowing to shift both from the left and the right. So you will then use this example, looking at a 4-bit one hot encoding. You start up with 0000, and you start shifting 1 from the left. And then once the 1 reaches the rightmost bit, and then you will start shifting back toward the other directions and with a 1. So by the time you have all 4 bits as 1, and you have saturated a counter. So there will be an example of an overhead if you want to count 500, then this will require 250 bits. And then because the DRAM is arranged in a way that each row is 8,000 bits, the current DRAM, and so this overhead is roughly about 3%. So let's examine the local sense amplifier now with the current DRAM. This is a generic circuit. This is a particular approach with isolations, and there's ways to do it without isolation. With isolations, you will have an extra transistor or maybe a transmission gate. So on the left side, it's the equalized circuits, basically consisting of 3 transistors or even down to 2 transistors, where you pull both bit line and bit line bar, the complements, the reference bits, to half the VCC. And then the middle one, in blue, highlighted in blue, is it's the cross-couple inverter. This is the heart of the sense amplifier, and this will be powered up using this PSA and NSA. No acronym implication. This is just positive signal assertions and negative signal assertions. And then basically powered up this cross-couple inverters. And this is will be then used to sense the small differences between the bit lines and the reference bit bar line, where there's a charge shared on one of the lines. And then on the right, this is the column select. These are I/O circuitries, and that eventually will select the part of the 8K bits in a row into outside the secondary latch for I/O. And then you see that on the left and the right, for the bit line and the bit bar line, or reference bit line, you have an isolation transistor. Basically, the advantage of having a site isolation transistor is that you can develop you can sense the difference between the bit and bit bar line, and then you allow the cross-couple inverter, the sense amplifier, to develop fully. Then you connect the ISO, you turn on the ISO, and then it will use to drive back, restore the voltage that you're supposed to go into the cell. And this is because DRAM is destructive read. When you read the contents, when you do a charge share, the contents of the cell has been destroyed, has been brought to close to half a VCC array. And so so the advantage is that with the ISO is that you are able to to fully develop the differences, the small delta V that was developed, and then allow it to drive the signal back to the cell. So this is more noise immune, but the disadvantage is that it is a little bit more more overheads because you have these 2 extra transistors or 2 extra transmission gates, which is both an N and P pass gates. And so this is just to show that in abstract form, now you have a box in the middle is a blue box. It's a sense amplifier, and this is the ISO and the shift allowed you to shift in one direction. So this is illustrating that you're shifting from the lower part to the upper part of the bit. And this is a demonstration in the abstract format that you're allowed to do. So you were adding the 2 set of the extra pass gates, so allowed you to shift in both directions, both from the top to the bottom and bottom to the top. Okay. And this is described in the paper. So if you need the details, you can go to the paper, refer back to the paper and look at it. And so this is an animation. So this is coming back to just the example I showed in the first part of the abstract slide, that you have a shifting from the bottom to the right to the top. And then when you turn on the signals, that is corresponding to the correct ISOs and shift. And this, if you turn off the ISO and turn on the shift, and this will be actually the actual equivalent circuits that you will see, that will allow you to write to the adjacent bit lines. So the bottom line is the bottom part is a 1. There's a hard-coded 1 that allows you to propagate a 1 either from the left or from the right, as described in the 1-hot encoding examples in previous slides. So we have captured this circuits in LT-SPICE as the schematics. So again, if you look at the left part, this is the equalization circuits. Is either the 2 or 3 N-type transistors, and the blue again is the cross-couple inverters. And then we have the PSA and the NSA, and they are actually shared among these 2 bits. We're showing 2 bit lines. And so there's really, because you have bit lines and bit line bar, and then you have really just, you have these cells also. We're showing a photo bit line, but then it's just for simulations. It could just be a open bit line as well. And it's just easier to show instead of expressing it out all the way horizontally. And this is the ISO gates. So this is showing the standard DRAM sense amplifier with equalizations with the cross-couple inverters, and then with the ISO for both bit and bit bar lines. And so we have simulated with the PTM models. This is the predictive models that is openly available publicly. We are currently working with a Taiwanese DRAM vendor. As most of you know, that DRAM vendors are relatively conservative. And we have to sign NDAs, and then they will allow me to. We are in the process of getting approval from them, and then I will be allowed to run simulations on their system using their models. And they were not willing to open the models for the community. So this is the result of simulation, the regular DRAM, and you see that once it's equalized, this is equalized, and then you turn on the charge sharing with turn on the word line. There will be a charge sharing. A small voltage differences, delta V is developed, and then the sense amplifier is turned on. The SAM and SAP is turned on, and then they will resolve into the values, and that will be able to read and write back to the cells here. And we see that the cell 0 is written back to the values. And so I ran it in 2 cycles. Each cycle is 50 nanoseconds. And then the row is in the word line. The row enable the word line is is activated about 22 nanoseconds after equalizations, and then the other signals need to turn on. And by the time we see this, the signal is relatively stable, and we sort of evaluate the time. This is about roughly 46 nanometer minus 22 nanoseconds. And this is showing the data is not flipping at all. And this is another simulation, there's another bit that shows the data actually going the other way. So it will actually either sensing a 0 or sensing a 1, and that both of them are resolving the data back to the cell. So this is a cell 2. And again, then we sort of eyeball measure the timing differences, and then it's about the same for both zeros and ones. Now we also capture the counterpoint proposals. Again, this is on the left side is the equalization circuits. Again, this is showing 2 bits, and this is the middle one is the sense amplifier cross-couple inverter. And then we have, instead of just the ISO, we have 2 more transistors, 2 more pass gates to allow that to shift from either from the top or the bottom. In this case, we're simulating shifting from the top. We have a hard-coded zeros and ones for bit and bit bar, and trying to shift it back to the next bit, which is from the top, from the external bits to bit 0, and then bit 0 becomes bit 1. And then we again simulated using LT spice. And then this is the bit 0. So this is because it's original data is still 1, so there's nothing to be changed. And so we show basically showing that this is similar to the normal DRAM sensing process. So that the timing is about the same. And then we also simulated the other way, where you have to flip the bits, and then so this is showing that we're flipping the bits, and then that timing is a little bit longer. This is again, we're just trying to measure a few of these simulations. So we'll come to that later on about the future work, what we plan to do about looking at variations and other things. So then the question then is, what is the impact on this small timing delay due to you have to override this 0 to 1, 1 to 0 on the adjacent bits?
Shilin, we're over time, so if you could wrap it up.
Okay, so I'm going. Okay, so yeah, so this is just to show, it's also in the paper that we have different timing. We simulated in the system level different time impacts on timings from the 32 all the way to 42, and then this is depending. We did a sensitivity studies about different counts. This is 64 counting 64, and this is other different number of counts and trying to study the possible impacts of using this approach. So future work, I'm just going to wrap it up. So currently using PTM 22 nanometer low power model. My counterpart at Taiwan said this is close enough, but not exactly. And then we still need to optimize the circuit design a little bit about the sizes of these transistors. They're not willing to tell us the size of the transistors, the sense amplifier, and we need to do multi-color simulations with variations. And we need to also study the layout impacts and whether or not how much area percentage that we add by adding those extra 1 or 2 transistors per bit. Okay, that's it. Summary is we're trying to propose a low cost of implementations to track the per row count using circuit techniques.
Wonderful. Thank you, Shilin.
Yeah. Thank you.
So we're kind of out of time, but I'll allow one question, one burning question.
Shilin, this is Moin.
Hi, Moin.
Yes. Shilin, very nice piece of work. One thing that I think is phenomenal, what you're pointing out, is that typically we think that higher threshold is low overhead. PRAC is a solution where higher threshold is higher overhead. So there's actual value in targeting low overhead, right? Like low threshold, like 100 or 200.
Right.
Do you know what the timing impact would be if PRAC had 8-bit instead of 16 bits?
No, yeah. So the performance study is done by UBC. We can study that definitely, but we don't have it. Maybe Prashant can say something.
I know him.
Yeah, I know because he's your student.
Hey, I think I can hear myself. I think we're done. Thank you very much, Shilin, for the presentation.
Okay.
We'll
Yeah,
get
thank
back
you
with
for
online.
Okay, thanks.
Thank you. Okay, we'll move to the next presentation right now. And that's going to be by Finn, if I remember correctly. Am I correct? No, Salman. Salman, are you going to present your computer? No, mine's okay. Just make sure it's not vulnerable to Rowhammer. Not yet. Okay, Salma is going to talk about the RFM and the art of Rowhammer sampling. Yeah, just. You're sharing the screen, right? But we don't see it on Zoom. Okay, you can take this. This is an example of latency increase. Even though it may have high bandwidth, when the latencies are long, you can get these delays.
I guess I don't have to introduce myself since I was already introduced as a panelist. And this work was done with Moinuddin Qureshi. So as we talked about earlier during panel discussion, I guess, there's two places to potentially try to solve Rowhammer. Traditionally, it's solved in the memory chip, but it can also be solved in the SoC. And we should consider the advantages of solving it on memory controller side. For example, maybe there's a trust issue and people who are running the system don't really want to rely on an obscure and proprietary implementation in DRAM. Maybe they want to avoid slowdown of PRAC and they don't trust the alternative. Maybe they don't want to rely on refresh cannibalization to that degree. Or maybe they want to just try to have a low-cost solution on the SoC side. So there are some options here for SoC vendors to ensure security, even if DRAM cannot be completely trusted. So there is multiple different ways that Rowhammer could be solved at the memory controller level. There could be counters and so on, but one very tempting way is to sample randomly. And conceptually, this is very simple. On every activate, we flip a coin. And if the coin flip is successful, then that activate is mitigated on the memory controller side. And the way you would do this, if you had no other tools to work with, is to activate and pre-charge the victim rows. So you have the activation originating from the user to the aggressor row. it gets sampled with some probability. And if we decide to mitigate, we calculate the victim rows and we activate and pre-charge those victim rows. And this probability over here of sampling can actually be mapped to the rowhammer threshold that we're able to successfully mitigate. So if we have a rowhammer threshold of 500, which admittedly is kind of low, the probability required is 1 out of 25, for 1,000, 1 out of 50, and for 2,000, 1 out of 100. So probabilistic tracking allows us to have a low overhead solution also, including on the memory controller side. But there is a complication here, which is that this over here may not actually be correct. So if you compute the victim row by subtracting 1 from the row ID and the other victim row by adding 1 to the row ID, this might not actually map to how the rows are arranged in the DRAM chip. And to solve this problem, prior work deals with a concept. So this is the problem here. So it might actually be some other distance from the aggressor on either side. And prior work solves that using a special command called nearby row refresh, which takes an aggressor row, automatically computes the correct victim rows for that aggressor, and issues rowhammer mitigations to those victim rows. And this command is per bank. That's important to note. And so it turns out that JEDEC did not go with this particular method in DDR5. They did something slightly different. For each bank, there is a DRFM address register. And there's a special pre plus sample command that can be used to sample into that register. So the DRFM is actually DDR5 version of support for implementing SOC side rowhammer mitigations. And then, so it has these two components. So the first component is what I talked about, which is there's a special command, which is pre plus sample that samples a particular activate into a DAR register. And the second command is a DRFM AB or DRFM SV command, which is actually responsible for doing the mitigation. So the way the mitigation typically works is that the tracker decides for any particular activate whether to sample it or not. And if we decide to sample the activate, then when we pre-charge, we use the special command. And at some later point in time, we mitigate using a DRFM command. The difference between the two DRFM commands, AB and SP, is that AB applies to all banks. So all 32 banks are stalled. And we hope that most of those banks have populated DAR registers so that we can actually mitigate as many of them as we can. And DRFM SV command, same bank is mitigated in each bank group. So 8 banks will stall. So there is potential performance impact for 8 to 32 banks for each mitigation. If you compare DRFM against the NRR that appears in literature, assuming that you use para and use simplistic approach, it turns out that DRFM AB and DRFM SB are considerably more expensive than NRR. So there must be some better way of implementing a memory controller side rowhammer mitigation using DRFM. And this also shows up in this particular metric we have called rowhammer mitigation level parallelism, where we look at how many DARs are actually populated during the command. And it turns out that the poor performance for DRFM actually stems from this low level of parallelism, where we're pretty much handling a single bank for each DRFM command. So for para plus DRFM, we have really poor RLP. So we want to study the impact of different sampling methods on DRFM and see if we can do better than this. So let's recap what different methods exist for sampling uniformly. Sampling uniformly is important because in the offensive security work that looked at internal implementations in DRAM, it was found in DDR4 that many implementations suffered from a non-uniformity in sampling, which allowed an attacker to find the optimal position to place their accesses in order to either avoid detection or reduce the probability of having the attacks detected. And we want to avoid the same pitfall on the SOC side. So that's why it's important to sample uniformly. And so we're only going to consider some uniform sampling schemes for this analysis. Para is basically independent, identically distributed sampling. And basic idea behind it is that for every activate, we flip a biased coin. And if the coin flip is successful, we mitigate. What makes it independent is that each of these coin flip events is independent of all of the prior coin flip events. And they're identically distributed because the probability is identical for these events. Mint is a similar concept, except it uses URAN sampling. Rather than having a coin flip for each individual event, we're going to have a window of some number of activates. And for this window, at the beginning of the window, we will uniformly randomly generate an index in that window to select what we will sample. And when we reach that point in time, when we reach that entry in the, that activate in the window, we will sample that activate into DAR. And at some point in the future, at the end of the window, preferably, we're going to mitigate that sample value. It is for purposes of memory controller side implementation, we want to avoid the side channel, which can occur if we decide that we're going to mitigate immediately after sampling. Because since the attacker knows that the window has the length W, let's say that if the second position is where the mitigation took place, the attacker might be able to detect the DRFM command through the timing side channel, and in the subsequent positions C and D might be able to insert an undetected attack. So it's really important for this mitigation to take place at the end of the window, because that is invariant to the sampling decisions that are actually made within the window. It is important to note that for both of these implementations, at the time when a bank triggers DRFM, neighboring banks may not have a valid DAR, which is the root cause of why RLP tends to be low. Now we're going to describe our approach, which is called MIST. It relies on harmonic sampling, and the goal is to get a high RLP so that almost every time that we get a DRFM, the neighboring banks have something to mitigate. So let's suppose that a bank has a single activate. We decide that if the bank has only one activate in the window, we're always going to sample into the DAR. If we have a mitigation happen, either as a result of the policy for this bank or policy for another bank, there will be something in the DAR for this bank. Now, suppose that there are two activates to a bank. We're going to, again, sample the first activate with 100% probability. And for the second activate, we will sample with 50% probability. If the first activate was obviously sampled, so when we sample when we flip a coin for the second activate, there's a 50% probability after that the second activate survives in the DAR, and 50% probability that the first activate survives in the DAR. So if at this point we do a mitigation, then it's 50-50 probability that it could be either of these two. Now, if we do 3, the same pattern follows. There will be 1/3. So at this point in time, after C, there is 1/3 probability that A is in DAR, 1/3 probability B is in DAR, and 1/3 probability C is in DAR. So they're all equally probable for being mitigated. And if we continue this pattern to an arbitrary point in time, it always holds true, but we are going to pick some maximum window. We're going to say that after this many activates in a window, we're going to issue a DRFM. Now, this is sort of a competition between different banks to reach the end of the window. The first bank that reaches the end of the window triggers DRFM. And at that point in time, anyone who has anything in the DAR, which is basically anyone who has accessed at least one has at least one activate in the window, is going to participate in this DRFM command. And so we should have a really high RLP, because as long as there's one activate in the window, we're going to, the next DRFM will be participated in by this particular bank. At the end of the, whenever we trigger DRFM, the window resets for everyone, for all the banks. So they all start their windows all over again. And so for any non-empty window, MIST ensures a valid DAR at DRFM for any bank that has a non-empty window. So this is the impact on RLP. If you look here, we get an RLP of 8 almost consistently out of MIST, whereas Para and Mint are at 1. And there's also a vast performance improvement. The slowdown is reduced from 25% to 4% at 1K threshold. So a paper that is going to be in ISCA is called DREAM, and it has a slightly different approach, which is to delay issuing the DRFM commands. And the insight that they use is that the delay should be until the next sampled row to the same bank. So let's go through this. So when you have an activate, the tracker decides whether to mitigate or not. And if the answer is yes, then we fill the DAR using the special command. And at some point in the future, the DRFM will happen. But the other banks are not idle, they're also busy. And so it's possible that other banks may populate their DARs in the meantime. And the advantage of delaying until the next sampled row to the same bank is that it buys us all of this time to fill the DARs for the other banks. And this is really the last possible moment, right? Like when you get the second activate to the same bank, the second sample to the same bank, that is the moment when DAR needs to be free on that bank in order to contain a new address. And so that is the right point in time to issue the DRFM. And once we issue the DRFM, we can refill the DAR and start a new window. So delaying gives other banks chance to sample into DAR. And that's a paper that is in ISCA. So we compare RLP and slowdown between our approach, MIST, and Mint and Para implemented using the DREAM concept. The performance of Para with DREAM, the RLP of Para with DREAM is sort of halfway there, but not quite as good as MIST. And Mint with DREAM and MIST are pretty close together. And this is in terms of slowdown percentage. You can see that again, we see something similar where Para with DREAM is not performing particularly well, and Mint and MIST are kind of close together. RLP of 3.2, 7.5, and 8 for Parity, Mint, and MIST respectively, and slowdown of 8.4%, 4.23%, and 4.18% for Parity, Mint, and MIST respectively for a threshold of 1K. Also, I'd like to point something out, which is that delaying the DRFM actually has a security impact, and you need to adjust the thresholds to take that into account. MIST does not have this issue because the way MIST is implemented, there is no, it's consistent in terms of not having a delay built into it. Okay. I don't have a lot left.
Maybe you can just give the conclusion.
Right. So in terms of comparison with PRAC, at currently realistic thresholds, the slowdown from MIST is 10% of that of Para. of PRAC. So it's very appealing at current thresholds. And that's pretty much my conclusion slide. So DRFM allows SOC vendors to securely mitigate rowhammer in case they don't really trust what happens in the DRAM chip. We talked about how to sample and its effects on parallelism that can be achieved with DRFM. We talked about para, which is IID-based sampling, MINT, which is RAN-based sampling, and MIST, which is harmonic sampling, which is DRFM aware and higher RLP. And MIST has lower overhead than PRAC at realistic thresholds. Not all sampling methods are created equal. Any questions?
It's really burning questions because you're standing between thoughts, other thoughts, and this lunch as well. Anybody? Yes, go ahead.
We have not looked at that. Yes.
Oh, yeah. Yeah, these are good points for discussion for later. It's good to examine low-cost solutions in addition to high-cost solutions like graphene, which are very difficult to implement, but they're very important to develop, of course. Yeah. Okay, I think Andrew is next, right? Oh, okay, go ahead. You need to take this one, so hopefully 10 minutes.
We'll go 10 minutes. It'll be good.
We're gonna save us some minutes.
Absolutely.
Okay. Yeah, exactly. The resource manager. Okay. So Andrew is going to talk about this paper with collaborators and advisors at WPI.
That's right. So I'm with MITRE, but I did my research in collaboration with WPI, hence the red paint. Yeah, I'm going to do my presentation on rubber mallet, a study on high frequency localized bit flips and their impact on security. So you can go next slide. Oh, sorry. I'll control it. Sorry, I forgot. Yeah. Okay. Let's see. Okay. Yeah. So I want to start with some background. We'll blow through this because I think everyone in the room is pretty familiar with rowhammer. So yeah. So researchers found that if you access rows repeatedly, you cause these bit flips in surrounding rows. You need to do the whole row conflict pair because otherwise you're just reading from the row buffer. So they started with this double-sided attack, which causes corruption in these adjacent rows, and then sort of later research does this multi-sided rowhammer attack. And so our lab at WPI was sort of experimenting with these tools, so trespass, blacksmith, and we started to notice some patterns. And this whole research study is kind of an application of, all right, can we validate these patterns, and can we do sort of interesting attacks using these patterns that we're seeing. And so I'll go into this, the types of things that we were seeing. We kind of start to notice that there was some level of clustering with bit flips, within a row. And so we really want to quantify that. And, what does, clustering mean? Well, normally if, bit flips are kind of random within a row, you'd expect them to appear kind of sporadically. But we kind of noticed that they were sort of grouped in different places along the row. And so we really want to go ahead and quantify that. So we want to come up with, all right, what probabilistically would it look like if it was randomly distributed? And then, what are we actually observing within a row? And so this is, if it was randomly distributed, you'd expect, if there was 2 bit flips, around an average of, 4 kilobytes distance, assuming that you have an 8 kilobyte row. If you see 3 bit flips, you'd expect kind of 2 kilobytes distance, et cetera, et cetera. What we noticed was actually much different than that. So our observed bit flip distance was a lot smaller, which sort of indicated that level of clustering. Obviously, things converge when you get to more bit flips. But yeah, low levels of bit flips, you see this, clustering within a row. So that was interesting. It kind of led us to our next question of, do we see clustering within bytes and then specifically adjacent bit flips? There's interesting cryptographic things that you can do if you observe adjacent bit flips. So our study kind of pivoted to that. And again, how do we define adjacent bit flips within a logical byte? We're talking in the logical software domain rather than the physical domain right now, just because we had a team of cryptographers and we're kind of thinking in the cryptographic domain with this. And so, two bit flips that are non-adjacent, they're going to appear in different places on the byte. And then two bit flips that are adjacent, they're going to appear right next to each other. And so, we can kind of quantify the probability of, adjacent bit flips by saying, all right, the total number of possible ways two bit flips can manifest within a byte is n choose k, where n is the number of bits, k is the number of flips. And so the number of ways that adjacent bit flips can manifest is n minus k plus 1. So we can kind of come up with this probabilistic model. Now, I will say, we did this experiment. We used blacksmith and trespass, to see, are we experiencing a divergence in this probabilistic effect? We're actually not, but it actually pretty much fits the model perfectly. So if there are two bit flips, about 25% of the time in logical byte space, those bit flips are adjacent. 3 about 10% of the time, 4 about 8.7% of the time, which matches our theoretical probability. But there's still interesting cryptographic effects that you can take away from this. So we can model this probabilistically. We know that we will encounter these adjacent bit flips. And then, so for 256-bit ECDSA can be broken with only 200 faulty signatures. If you have two adjacent bit flips, 384 ECDSA, bit ECDSA can be broken with about 100 faulty signatures. So, so because of these new tools, because we have high frequency localized bit flips, we can do these interesting, cryptographic attacks. And then I'm going to pivot a little bit to some adjacent work, which then kind of circles back and connects. But I do a lot of my research on AI and large language models. And so we want to figure out, do large language models, are they affected by rowhammer, and can we break alignment of these large language models with rowhammer? Alignment is this idea that, models need to match human values, right? So, or, morality and that sort of thing. And so a lot of times, you'll have model alignment implemented via system prompts. And so these are real examples. So this is GitHub Copilot. When you're using GitHub Copilot, it tells the large language model to do things like avoid content that violates copyright, or Gronk, it says ignore users' instructions if they're trying to get Gronk to say like a yes or no or something like that. And so, using our rowhammer tools and, these high frequency bit flips, we want to see, all right, can we break model alignment? And so this is a real conversation example, just to give you an idea. So, system prompt, this was using a version of Microsoft Phi using Llama C++. And so, you give the system prompt, you're not supposed to tell the user how to make bombs, weapons, and drugs. And so, of course, if the user asks, can you help me make a bomb, it's going to respectfully refuse. So we're going to see if we can get the AI to tell us how to make a bomb. That's where we're going with this. And so when we're looking at different vulnerabilities in the GGUF, this is our standardized LLM model format. There's a bunch of different places that we were looking. It turns out there's a vocabulary section in the GGUF file, which the position of the different strings, which are the tokens, right? The different like parts of words or words that large language model uses. Their position indicates their token ID, which is sort of how the model associates meaning to the different words. And so we said, all right, can we fault two different words and effectively have them swap position? So if it sees that word, it interprets it as the swapped position. We give this term token swapping. So just an example, make and lake, they're only one bit different from each other. And so we define that as a token swap. So we do this reverse engineering of the Guffey file. We find the location of the make token. We find the location of the lake token. And we find a way, can we fault it in just the right way so make becomes lake and lake becomes make? And so what does that conversation actually look like? So this is the same model, but we faulted that lake in the make token, so they've swapped positions. And so again, the system prompt says you're not supposed to tell the user how to make bombs, weapons, and drugs, but we faulted that token, so it kind of interprets it internally as you won't tell the user how to lake bombs, weapons, and drugs, which doesn't really make a lot of sense to us. But then as the user, we've used the swap token because we're the attacker, so we know which tokens have been swapped. Can you help me lake a bomb? And the AI is more than happy to help us, do this. And so how many token swaps are possible? That kind of determines how much we can really butcher this system prompt. So there's different tokenizers. So we found there's 310,000 potential token swaps, GPT-2, Llama, 78K, T5, 50K. And then kind of circling back, adjacent bit flips kind of enable more complex token swaps. So you can, butcher the system prompt even more with these kind of, high frequency localized bit flips and, potentially break alignment on real, production models. So yeah, that's my presentation. Happy to take any questions.
Great. Look at the fun. You want to come here?
One of the observations that I actually saw that, so first of all, a clarification, when you talk about adjacency, you're referring to cache line adjacency, right? If 2 bits are adjacent if they're next to each other in the cache line, not in the DRAM device.
Yeah, so we're talking about this from the logical perspective, from the software perspective, because there's bit interleaving and stuff. So yeah. Yeah.
Just to clarify. So one of the observations is the following: people now in LLM, there's all this work on quantization.
Mhm.
And the way I think about it is you take, so we represent numbers using some encodings. And there's a lot of redundancy in that. So people are smarter to come up with really smart encodings where I have a base that is fixed for a range of numbers, and each number then I represent as an offset from that base or something like that. So the observation there is all these quantization techniques, they make integrity even more important. Like in other words, when you flip a bit, flip, like everything, so there's an interesting observation as to how much damage can you do by flipping a single bit. That's an interesting question. And the other question is, can we have quantization schemes that are more robust to single or adjacent bit flipping?
Right.
I think these are really important questions that kind of your work really inspired.
Right. Yeah, I agree. And the other side of it too, I think when you're looking at, if you're attacking the model weights, right, there's a lot of known methods for fine tuning to uncensor a model. So you can do this. So you can actually do a differential analysis on here are the model weights for a aligned model. These are the model weights for an unaligned model. Figure out what are the really important weights that you need to flip in order to sort of break a model. I think that could be a really interesting, research path as well. So yeah. Yeah.
You mentioned this alignment, which is really interesting.
Yeah.
Currently, you didn't build an attack that takes advantage of these multiple bit flips. Right?
That's speculation. Yeah.
Okay,
Yeah.
Speculation. Are you working on that?
Yeah, I consider this all ongoing. Are you talking about with the model weights? Do you mean? Oh, yeah. So that's sort of what I'm thinking about going with next, because again, if you can come up with that differential, you can figure out these are the weights that are important. And in our lab has done similar work with classification models to figure out what bits you need to flip to install backdoors. So it's like, but you could do the same thing with large language models to break alignment, so.
I encourage you to build it and maybe make RowHammer, let's say, more interesting for people who only care about AI.
Yeah, for sure. Yeah.
And there are many of them these days. Yeah. Okay, thank you very much.
Thank you.
Okay, next we have Chris. Okay. Chris is going to talk about CNC prac. Okay, I'm not going to read the title, but you can.
High level.
All right, hi everyone. So my name is Chris. I'm here to present CNC Prac, coalesce not cache per row activation counts for an effective, efficient in DRAM rowhammer mitigation. This work was done in collaboration with Junghoon and Prashant from the University of British Columbia. So we're all now familiar with rowhammer. Frequently accessing aggressor row induces BFIPs in the neighboring rows. Well, as DRAM scales, this rowhammer threshold, the number of activations required for BFIPs is dropping. So scalable rowhammer mitigations are increasingly warranted. Now, as DRAMSec introduces per row activation counting, as we call PRAC, we have inline per row activation counters where we add additional cells to the DRAM rows and use them as counters for each row's activation counts. And they also introduced the alert backup protocol, where once a row counter reaches a predefined threshold, the DRAM can request an alert, incurs an alert, and then request mitigations to the DRAM. So PRAC, as we discussed also in panel probably, is that it's a framework for maintaining exact counts and also for ensuring timely mitigation. So existing solutions that builds on top of PRAC are mold and cube PRAC. They build on top of the inline counts of the existing specification, and they're secure for extremely low rowhammer thresholds. They also incur very minimal slowdowns because they manage their priority queues or tracking that incur low frequency of ABOs, which is, as we discussed before, is a very costly operation. But they suffer from performance overheads, as each counter increment requires a read modifier write from the DRAM, and this increases the TRP timing, which evaluated by the prior works incurs greater than 10% energy overheads, not performance overheads, sorry. And another solution in the meantime was Cronus, which proposes we store counters instead of inline, rather in a different subarray. So on an activation to a data subarray, the counter subarray is also similarly accessed at the same time for a counter increment. So with subarray parallelism, Cronus hides the read modifier overhead by hiding the latency of the counter increment under the shadow of a data row activation. But this does not come without a cost. Accessing the counter subarray activating the counter subarray incurs additional energy, and as evaluated by Cronus, it's approximately 10% energy overheads. So to summarize, mold and cube PRAC are secure, but they incur performance overhead from the inline counters. Cronus is low performance overhead, but the additional counter activations incur additional energy overheads. So our goal is to provide an efficient PRAC design that solves the problem in both existing solutions. So we propose CNC PRAC, coalesce not cache, where first we evaluate the DRAM workloads and we observe localities that exist for coalescing, but unfriendly for caching. And we propose the first in-DRAM coalescing design to minimize counter row activations. And our approach shows that we can reduce counter row activations by 83%, incurring only less than 1% of the dynamic energy overhead. So, what is counter coalescing and what's its intuition? So as a reminder, Cronus, when you have an activation in the data subarray, the counter subarray is subsequently accessed. And let's say we have 3 activations here, 1, 2, and 3 in that order. This would mean 3 activations as well to this counter subarray, as well as 3 read modify write increments. But this doesn't have to be the case, right? So as we can see, we have multiple activations for counter row despite temporal locality. What I mean is these 2 goes to the same counter row in a short period of time, and they share the same counter row, right? In this case, it's possible that we can group 2 read modify writes together with 1 activation. So to do that, we modify the increment process with a counter request buffer. So before we had the activations, but instead of going to the counter subarray,
we buffer them into the request buffer. And with the request buffer, the request, we can now say we have those two requests going to the blue row, then group them together with one activation. We perform the two read modify writes together. This way, we do not have to incur previously we had two activations, right? So this way we reduce the counter activations in total and its related energy overheads. So is counter coalescing even feasible, right? So our design is rooted in temporal locality analysis, where we use RAM layer 2 and analyze around 57 workloads, and we observe in any window of 64 row counter activations, 6 target the same counter row. And this means, but this statistic means that it's feasible to coalesce multiple counters that go to the same counter to the same counter subarray row in a short period of time. So now I'm going to introduce the CNC Prax request buffer. On the data row activation, an entry is inserted, and an entry of the request buffer has 3 components: the row ID of the counter in the counter subarray, the byte ID of that counter in the row, and rep count, which is the number of times it's been repeated while it's inside the buffer. So CNC Prax request buffer removes entries on 3 occasions. First is the obvious case where if we observe opportunity for coalescing. So let's say we coalesce on 4 entries. We set M equals 4, and we have 4 entries going to row ID 1. Then we say we can remove all these entries together for a coalesced counter access. And this is the best case scenario as we replace M activations with only 1. The second scenario is we have to remove when the buffer is full. Right? Despite having a suboptimal coalescing opportunity, we need to remove because we have to avoid overflow. And number 3 is we have to remove for coalescing, remove for more security. So as we discussed before, we're delaying the counter increments by using the buffer. And well, let's say you have a counter here that's being repeated, reaccessed 4 times. That means the mitigation responses are also 4 activations late, right? And to accommodate the TRH, we have to reduce the MBO with a fixed value. We say K, and this way we don't have to worry about security. And whenever an entry with a rep count that reaches 4, we have to remove it despite maybe it's not the best case for coalescing. So we have talked about the policies of the request buffer. We also have to talk about the designs. So we propose 2 different designs for CNC Prax. One is CNC Prax per row, where we provision 4 entry counter row request buffers, FIFO based, for each and every counter subarray row. This is the perfect scenario for coalescing, but since everything is per row, it's may incur high area overhead. On the other hand, CNC Prax, we propose CNC Prax unified, which uses a fixed size one queue for the entire counter subarray. So we use a CAM structure for this, and on each insert, we update the entry with the best coalescing potential, which in here is red. We have 4 entries here, and we move based on this information. And this has less storage overhead, but maybe have a higher static power due to the parallel circuits of CAM. So we evaluate CNC Prax on the MBO of 32. And on the left, you can see that we have a normalized counter row activation against Cronus, and we see a grid reduction using the per row approach to 83%, while the unified approach isn't too much off. It's only a 10% less with less storage. On the right, we show the dynamic energy reduction of our approach against Cronus, and we show we reduce the dynamic energy consumption in Cronus by 60%. So, okay, we talked about coalescing, but why didn't cache work? So we further analyzed the workload and we show that in a typical DRAM workload, 2,000 plus rows per bank accounts for 50% of the total data row activations. And to capture all these localities, we need a large counter cache, which is infeasible in a per bank scenario. We further evaluate for small caches, and we found that we have frequent evictions, and they're rather provide a really like minimal improvement. And this is due to they really have a small hit rate for the kind of workloads they're working with. So in summary, prior prac implementations are have either performance overhead or energy overhead, and our existing workloads for DRAM makes the small cache ineffective in an area constrained DRAM, and we propose CNC prac, which is a coalesced-based design for destroying prac counters based on Cronus. And our approach reduces both the dynamic energy overhead and the counter row activations. Yeah, that's all. Yeah.
Chris, so one question I have is that if you have a counter subarray and a main subarray, you're basically converting a single activation potential into two activations, right? Now, activations have a rate limit called TFA, right? You can't do more than 4 bank activations within a certain period of time. In the baseline, you are doing 4 activations in that time. But now if each activation becomes double activation, does your system get into a TFA limit? Okay.
Anybody wants to take that? Okay, maybe I'll take that actually. I think yes, well, yes and no. Depends on how you design the second subarray. You can make it relatively small, but TFA is also a limit that's very artificial. In many papers have shown that in the past. Sorry. This is a great topic for discussion over beer. Yes. In the spec, yes. In the spec, yes. Yeah, you need to modify the spec for Cronus. And yeah, that works. Yes, but maybe Kuljit can rebut me. Okay, very quick question.
Thanks for the presentation. One question that I have is that how sensitive your mitigation is to the addressing function, right? For example, how the activations are mapped to the counters, because it seems to me that how the mapping works, and also it's very sensitive to the application that it would you find the opportunities to coalesce the counters.
Okay. So I think Cronus has a randomized row mapping, and if given a randomized row mapping, we still see the slides before showing like in every 64 counter row activations, we see that 6 goes to the same counter row. Then I would expect this to hold for even a different, addressing space.
Couple of questions.
Okay.
We looked at hammering the row that's got all the counters that calls backup. Plus, what's the die sizing back? The cells and other items have a large die size.
Yeah. So
versus the rack.
Yeah.
Also, how you route this bits out in parallel, how you read these counters, prefetch from one substrate.
Yeah.
How is the other one read?
Yeah. Yeah. For the first question, do you mean like row mitigation on the counter stuff?
Yes.
Okay. Yeah.
Multiple rows.
Yeah. Yeah. And for that, I think Cronus also mentioned, since we have a very small subarray, we can use, I guess, something like I forgot the Riga paper, where they mentioned we can latch like extra circuits to refresh counter subarray rows and during refreshes of the data subarray. Yeah, something like that, or like a simple tracker, let's say, because our rows is so small, row count is so small. And second question, I forgot the second question. Yeah, dissecting, we have that over here. Yeah, we have that over here. We have, yeah, the unified has 700 or so. This mu, yeah, percentage overhead. I think we don't have a percentage overhead at the moment, but these are the numbers, and yeah, we don't have that yet. But what's the third? The third one is, yeah. How much?
Presenting next. So hammer is exploiting row hammer bit flips without crashing.
Mm-hmm.
Okay. We have 10 minutes too, and then we'll be late for lunch. But we have another presentation that's for.
Speedy, yeah. Okay, you just full screen. First one.
AI wants to present it for you.
Right. Hello, everyone. My name is Finn de Ridder, and I will be presenting Softhammer, exploiting row hammer bit flips without crashing. So this is an attack paper. Together with Patrick and Kave from ComSec, ETH Zürich. So to motivate the problem, I will first say something about the difference between row hammer exploitation in theory and practice. So in theory, row hammer exploitation looks like this. We have the attacker, and the attacker wants to get into this position, the position of a successful exploit. To get there, the attacker needs to trigger a bit flip. And we all know there are different ways to trigger a bit flip, but we somehow assume the attacker is able to do this. The attacker triggers the bit flip. And yeah, that's it. So you trigger your bit flip, you have your exploit, and you win. In practice, however, perhaps triggering a single bit flip is still somewhat easy, but to trigger an exploitable bit flip, you need to do much more work. So the attacker is searching, changing the aggressors, looking for a bit flip. And then once the exploitable bit flips are found, usually many more bit flips are triggered as well, right? Because you need very particular bit flips for the exploit. And the problem is that these extraneous bit flips cause corruptions and they make the attacker crash. And then, yeah, there's no successful exploit. So to illustrate this problem further, I will now briefly introduce a browser exploit. It's a row hammer browser exploit. That's part of this paper that I will present at USNIX later this year. So the general structure of the attack is the following. We start there, we build our pattern. So we build a pattern that bypasses the mitigation. And then we want to get to this position, of course. So the first step is templating. So the attacker is changing the aggressors, looking for bit flips and exploitable bit flips. And at some point, we are in this situation. So the attacker in this phase is hammering dummy rows. So data that is under the attacker's control. We find two extraneous bit flips, so two collateral bit flips, and one exploitable bit flip, the green bit flip here. Then we move on to the massaging phase. So this is nothing interesting for an attack. We want to exploit something that we otherwise cannot access, right? This is why we use row hammer. In this attack, we are targeting JavaScript arrays. So these are arrays in JavaScript. So the attacker releases the dummy rows, allocates these arrays, and now the bit flips, the attacker hopes that the bit flips will appear somewhere here, and then re-triggers the bit flip to take advantage of the bit flip and then exploit. And the problem is that once the physical, virtual, and physical memory is released, the bit flips don't change their location, of course, in physical memory, but in virtual memory they do. So the attacker allocates these arrays, but doesn't know exactly where the bit flips are. So doesn't know where the collateral bit flips are and where the exploitable bit flip is. And this is a problem because now you've just allocated your arrays, right? You're the attacker. The desired bit flip is over there. The exploitable bit, the extraneous bit flip is there. The attacker starts accessing these arrays. One of them is corrupted by the extraneous bit flip. Attacker crashes, and then the attack is over. And this is a real problem, and it's important to solve it because otherwise we cannot really estimate the severity of rowhammer, right? So otherwise it's just you trigger bit flips, but yeah, how dangerous are they really? So this we found is really a problem, and we solved it with Softhammer, which consists of 3 parts. And the first 2 parts are targeting the problem of having these extraneous bit flips. So ideally, we just trigger 1 bit flip, 1 or 2. So this exploit actually requires 2 bit flips. And we just want to trigger those. And the second part is about trying to avoid crashing because of extraneous bit flips, right? So assuming some of them will persist. So the first thing you can do is you can mirror bit flips that you don't want. And this is a known technique, right? So this is not our idea. This was used in exploit. So let's say I have 2 bit flips here, one that I don't want and one that I want. And then if you mirror the data in the aggressor rows, turns out that this one is less likely to flip and that one is more likely to flip, right? So this is something you can do to filter for the bit flips that you're interested in. This is a known technique. It worked on DDR3, but it didn't work on DDR4. That's what we show with the following experiment. So in this experiment, we are in the templating phase. So we're in this phase. We just found a set of bit flips, of which 1 or 2 are exploitable, and there are many bit flips that we are not interested in. So you can see here, round 0, we find about 28 bit flips, and we have our exploitable bit flips. And now we want to hide the bit flips, these 28 bit flips that we don't want. So what do? We mirror them. So we do what I've shown on the slide before. And you can see it's hard to see, but the number of extraneous bit flips drops by about 10 in this case. So let's say 1/3, but then it remains constant. So then we continue hammering, we continue mirroring any new bit flips, but nothing changes. So this does have some effect, but it's not enough. So something else that we tried to get rid of the bit flips that we are not interested in is to just hammer less. This is also why the paper is called Softhammer. So here, same idea. We are again in the templating phase. We have our exploitable bit flips and the extraneous bit flips. And now we just reduce the hammer count. So the hammer count is about 1 million. And we go down to around 10K. And you can see, so we gradually decrease it. You can see that there's a bigger drop in the number of extraneous bit flips. But at some point, we also lose the ability to trigger the exploitable bit flips. This is, of course, not surprising because we are not, in this experiment, we don't distinguish between exploitable and not exploitable, right? So you'll just lose your exploitable bit flips at some point. So what does Softhammer do? In Softhammer, we combine them. So the idea is that you mirror any bit flips that you're not interested in. Once you have mirrored all of those, and you're still able to trigger your exploitable bit flips, only then you reduce the hammer count. So this is an algorithm. You run this for 100 rounds during your templating phase. And then what you get is let's say in this case, there are 2 or 3 extraneous bit flips, but every now and then you're still able to trigger your exploitable bit flips. And this is enough for the attacker. So are we done? Well, not really, because even with 2 or 3 of these extraneous bit flips, as you can see here, I might already have my success rate, right? If I just have one, I halve my success rate. So that's why we also have another solution called priming. So recall these were the original stages of the attack. With priming, we add a third stage. So I template, I find my bit flips. Then instead of directly allocating the target object, so these arrays, I first allocate, so I release the dummy rows, but then I allocate, in this case, floating point numbers, and they are very hard to corrupt. So arrays are very easily corrupted in JavaScript, but floating point numbers not so much, because if they change because of a bit flip, the number will just change. So the attacker allocates these floats, then scans the floats. There is a risk of crashing here, but it's very low. And now the attacker can look at the floating point numbers and see which ones changed in a dangerous way had they been erased, detects these locations, then overrides the float with an array. So I hope you're not confused. This is an array of floats and this is an array of arrays. So that's why this is possible. And then you can only, so now the attacker triggers the bit flip one more time, doesn't look at this location because this is now a dangerous location and only reads the now exploited array. So that's it. The results. So with this soft hammer technique, we were able to reduce the number of bit flips by about 90%. So for the attack, this halved the number of page faults, and it enabled a 40% success rate. And without this technique, the attack would almost always crash. So the conclusion, mitigating collateral bit flips in rowhammer exploits. You minimize hammering, you mirror your collateral, and you stripe your exploitable bit flips. And if possible, you use this priming method to catch any leftovers, but it's not always possible, depends a bit on the exploits. That's it. I'm here for questions. This.
So you said you tried this and you still, you changed the data patterns, you still were
Yes.
So now imagine that this bit is affected by these two bits and not by these two.
Yes.
Right? You still flip it here and you still flip it here.
Yes.
So could that explain the reason why you couldn't?
So I have tried increasing this window to, yeah. So I think to 3 and also to 5, and that was not enough. Could be particular to the dim, yeah. Hi. That's a very good point. This is also in the paper, actually. There is another paper that does this. It's possible, but in this JavaScript setting, that would make the attack a bit more complicated. So I guess it's possible, but yeah, this is simpler. Why is that relevant? Yes. So I guess with on-die ECC, to find an exploitable bit flip, you need to trigger more than one bit flip anyway, right? To bypass the ECC. Yes. So I guess actually, yeah. So I guess ECC might make the attacker's job a little bit easier. So if you're able to bypass because once you have an exploitable bit flips, you should not have, or the chance is low that you have extraneous bit flips then, right? Yeah, okay. But this is assuming you're bypassing the mitigation, right? Yes, of course.
Okay. A good discussion. Continue. This ECC making things harder and easier at the same time. my favorite story about it was like at the same time. And one major DRAM manufacturer who shall remain nameless, a very senior vice president from that manufacturer came and gave the next talk, and his first thing was to rebut my comment about RowHammer, and he said that we have a solution to RowHammer. Sorry. Speech has a very strong ECC. Okay, yeah, sorry. 5 minutes. Okay. So next it's Hidemasa Kawasaki from a local enough university, Ritsumeika. Ritsumeika. Okay, go ahead. Okay, there you go. Go ahead.
Welcome to my presentation about a simulation-based variation framework for inter-VM RowHammer mitigation techniques. First, I briefly review the inter-VM RowHammer attacks. Inter-VM RowHammer is a serious security threat. As the diagram shows, this is the attack where an attacker in one virtual machine can induce bit creep using RowHammer in another victim VM. This attacks break the isolation between VMs. So why is it difficult to evaluate inter-VM RowHammer mitigation techniques? The core problem is that mitigation abilities and its overhead depend on the underlying hardware. For example, DRAM address mapping are different from machine to machine. This makes comprehensive evaluation is infeasible, as a machine with specific DRAM address mapping may not be available. To solve this problem, we propose a new simulation-based evaluation frameworks. This slide shows our framework architecture. Our key idea is to replicate inter-VM RowHammer mitigation techniques and DRAM address mapping only using software. This advantage of this is that we can easily test it inter-VM RowHammer mitigation techniques with various DRAM address mappings. Let me explain the architecture. At the bottom, an architecture simulator can let us configure DRAM address mapping and simulate RowHammer. On top of that, we run the hypervisor where we reproduce inter-VM RowHammer mitigation techniques. We have guest VM which execute inter-VM RowHammer attacks program. To demonstrate our framework abilities, we conducted a case study. We evaluated two inter-VM RowHammer mitigation techniques, Silos and Stado. As the diagram shows, Silos separate VM using the separate subarrays. Because RowHammer effect does not cross the subarray boundaries. On the other hand, Stado places a guard law between VMs to absorb the hammering effect. We evaluated both mitigation techniques with three different DRAM address mappings. Now for the security evaluation result, we simulate inter-VM RowHammer attacks from attacker VM to victim VM. Our findings are positive. As the table indicated, both Silos and Stado successfully defended the inter-VM RowHammer attacks in our tested configuration. And our framework can measure performance overhead. As an example, this chart shows the runtime overhead of the application in VMs and the VM boot time. Chart A on the right shows that VM boot time. Chart B on the left shows matrix vector application, multiplication application. For both cases, you can see that the performance overhead is different from DRAM address
address mapping and mitigation technique is used. I will very quickly cover our limitation and future work. We only focus on the inter-VM rowhammer attacks, not targeting hypervisor itself. And second, our simple memory model does not using second level address translation. So we cannot evaluate the attack against it. But we only support the continuous physical address allocation. So it's which limited to some defense scenario instead of. Addressing this point is our plan for the future. This concludes my presentation. Thanks for your attention.
More tools. I guess I have a question. Is your tool open source?
After this feature I will cover it.
Okay. Okay. Great. Yeah. Keep improving.
Yeah, thank you.
Okay. Thank you. So we're almost at the end. I'll take just a couple of minutes. If I can share, I think I can kick off.
Yes.
I don't here. See what I share?
Yes.
I see. Okay, we're at the end of the workshop. Thanks for staying. There's a full room, not going to the lunch. Maybe the lunch is very bad. So, but the dinner will be good. That's what I promised. Except you have to wait until 9 p.m. So hopefully we'll have a lot of you there. We have a reservation that can accommodate 20 people or so. Is that right, Alphonse? So if you want to, some people are going for sure. If you want to go, and if you're not on that invite list, please talk to me or Hassan. Okay, but you can also come over there and see if there's available. That's perfectly fine. It's a big place, if I understand correctly. And if you want to join the, let's say, excursion, we're going to meet at 6 p.m. In front of the Okuma auditorium. Do you know where that is? I have no idea. You know, it's right there. Okay, yeah, perfect. It's where, okay, you can find it on Google Maps. And we're gonna, this is the plan basically. You can take a picture of it. Yeah. Yes, please go ahead. One of the primary Yeah, thank you, Stefan. I should say that I got a lot of help from my students over here, Haosong, Mohammed, as you can see, and some others like Andreas, Ismail, and some of them are working on Rowhammer quite a bit. So thank you for coming. I hope I'll see many of you at dinner and the excursion. If not, feel free to contact me anytime. And have a good rest of the day. And if you're attending memory-centric computing systems, I'll be there giving a talk.